selling storage to a channel and just go buy it off the shelf. And there was this was a period of some of that dark times, because there was actually some really dumb decisions made internally by management when server guys came to us in storage and said, we need a box this high, this wide, this big, this fast, because that's what we need for HPUX. And some of the management that I worked for said, no, we're making a box this big, that wide, this fast, this expensive, because we're focused on going after this x86 market, so you can take this. To me, I thought that was like the dumbest thing in the world. We have a captive base of a server business, and here's this storage that they say they need for their customers, and our management was kind of more focused going after this other market. Problem was, what they targeted was right down the middle of the bowling alley. What they were targeting for x86 was actually too big and too expensive for them, and what we made was too small and not scalable enough for them. And we could have done a better job of satisfying both, but they decided to roll the bowling ball right down the middle. About I'd say 1996, 97, the server division went off and actually created an OEM relationship with what was then Data General. And they were OEMing storage from Data General, and this would probably be one of the lowest times of being in a storage employee in HP. When I would go to Cupertino to go talk to my server colleagues, they came to the front door and treated me like I had to wear a visitor badge, because I was considered, they wanted to treat me just like they did all their other OEM partners. So DG came, they got a visitor badge. Calvin from Boise came, and I got a visitor badge. They were very close to killing storage because, again, it wasn't meeting the needs, and we weren't doing that great. A pretty smart guy came along who was managing the server business and looked at this and said, wait a minute, we've got this great technology in HP. Why are we throwing all this money at other people? And he brought storage into the server organization and said, we're keeping this, we're going to develop it, and we're going to make a business out of it. So around 2001, that's when the Compact acquisition happened. Changed HP a lot. I mean, I won't go into the kind of what Carly did or any of that, because it's probably
a 2-day event.
Probably, yeah, you need a 2-day event on that one. But you know, the big thing was that Carly, I think, thought that storage could sell itself, and you don't need people that are smart to sell storage. And we recognized that was wrong. And storage started to tank a little bit, even though we had this great portfolio coming together between Compact, who had a really good x86 set of products, and HP had a great high-end HPUX focused set of products with the XP. And the coming together of those two actually really fit well. And it was one of the few parts of the acquisition where they kept both businesses. Most other ones, they took this business and they said, this one's gone. We'll take this one from Compact, this one from HP, we'll close it down. We'll take this one from HP and we'll close that down from Compact. Storage was one of the few where they put it together. So I actually worked, Mark Lewis was the head of Compact Storage when we bought them. I worked in his organization. My manager was from Compact, went to Colorado Springs all the time. Anyway, that coming together was great, but the problem was, at least in my opinion, HP underinvested in storage in a lot of ways, both in how they sold it and how they developed it. You know, we had a recent CEO. There's some few people, I won't say who, but you know, there's a few people that have said that he was burning the furniture. My perspective is that's exactly what was happening. He was burning the furniture, and that's when I should have left. That's when I should have gone to 3PAR. And at times I kind of think, why did I stay? I stayed because I love Boise, didn't want to leave Boise, and I still had a job. I wasn't going to go find a job in storage in Boise, and I wanted to stay in storage, so I stayed. So in some ways I think I was stupid for not leaving, but now you're going to see why I'm really happy I did stay. So things started to change a lot in 2009. Dave Donatelli came in. He came in with an attitude, we aren't going to lose in storage, we're not going to put a cow in a field with dead grass and see how long we can milk it for. We're going to actually do something for this business and invest in it. Tom Joyce, he hired to come. Tom Joyce was our marketing manager up until a couple months ago, actually. He's now the general manager and VP of Converged Systems. So Tom now has a new job. He's actually going to be here, I think, on Wednesday doing a keynote. So for you guys that are still here, I think he's got a keynote Wednesday afternoon at Nth. Those two guys, in my opinion, changed HP storage. They came in and they said, we're going to win. And they brought in an attitude of, we're going to kick butt and we're going to win. We're not going to take, you know, just good enough as an adequate answer anymore. What also changed is they actually got a strategy. There was a lot of years to me, it's been the best time to be at HP. So I'm going to just briefly just show you a couple of the vision slides. I'm going to not waste time on talking about that because I'll leave that for the rest of the day. There's three things that I think HP is focused on from a strategy standpoint. Dave Donatelli's organization really is focused on converged infrastructure. Converged cloud tends to be something that crosses Dave's organization as well as the public cloud folks. So that's a kind of a pan HP where this is Dave Donatelli's organization, and then software-defined data center, which that'll be something that you'll hear Dale Deegan talk about a little bit later this afternoon. I'll give you a little bit more on some of these. Converged storage, well, you'll probably hear David talk more about this on Wednesday, and I think everybody's staying for David. Is anybody leaving Tuesday night? Yeah, that's all right. You are leaving Tuesday night, so I think Ray's the only person leaving Tuesday night. But David speaks Wednesday just before lunch, and for anybody that has flying out on Wednesday, if you can stay for David, he'll, I'm sure, do a great job talking through this. I love the way he says polymorphic. It was fun in HP Discover in December when he started talking about polymorphic simplicity, and frankly, some of the bloggers that were in the room, their eyes rolled, like, really, you can make up a word and sell it. David's a very smart guy. He's the guy that came up with autonomic, and now everybody talks about how their storage is autonomic. Not everybody, but people that think they have autonomic storage, they use those words, autonomic. And really, what we're doing is, if you see the definition of polymorphic, it's existing in several forms, shapes, and sizes. So you think what we're doing, what we're focusing on is software that can run on any kind of standard hardware, and it provides these high-level data services. So we really are focused on having a single platform, primary storage from high-end to entry, and delivering a bunch of these kinds of benefits. And you really see that when PD starts talking about, and Vish talk about the three-part portfolio and how it really is a polymorphic platform. So this is a kind of just a comparison, a quick comparison. And PD, do you have this slide? Because if you do, I'm going to just fly past it.
Okay, Vish has this.
I do have this slide. Like, if either one of us can come.
Well, I'll talk to it just from a high level. I mean, this is just looking at EMC. EMC's got 5 platforms for primary storage. They've got 3 for information retention and analytics, and they've got 2 for backup. We'll have somebody here that can talk on each of the topics on the HP side, but when you look at what we're doing, now, clearly, there are other platforms in HP. We have an MSA, so I'm not trying to say that we don't have an MSA, but when you look at the meat of the portfolio from the entry, mid-range, all the way up to tier 1, it's one single platform. For information retention and analytics, it's one single platform. And then from a information protection, when we talk about a dedupe kind of environment for disk-based backup, it's a single platform.
I think, and I'll just to add a little bit to this. The customer said it to me once, I think pretty aptly. The man is about stock. I mean, HP, to be honest, had some of the same problems, right? So many different primary storage products, and I think if a customer has 10 architectures from one vendor and he wants to be dual sourced, that's 20, right? So that's what he said, the man has got to stop. And I think going forward, I'll show in my slide as well how we want to bring that very narrow focus to certain products.
Well, and it's probably a lot of the reason why those dark days of what I talked about before. I mean, it's just impossible to develop 5 platforms at once and invest in them all and have them be leading edge. EVA was a great product when it came out. Towards the end, when we bought 3PAR, I mean, there was a reason we bought 3PAR. And EVA is still there, and people are still buying it. People that love EVAs, but there's a lot of people that kind of start to get it now that time to switch. But I think there's a benefit to HP to have less platforms, but it's obviously the reason also is it's a benefit to our customers. Again, I'm going to fly through this because we'll talk more about this afternoon. This is just more of the why I'm excited, because there actually is a strategy. So we started talking about converged storage in 2010, and we basically told people it's based on 3 things. It's going to be built on industry standard servers, or industry standard platforms. It's going to be scale out with federated services, so meaning that these things scale out like a 3PAR scales out, like a HP Store Virtual, HP Left Hand scales out, like HP Store All scales out, and then has data services that platform provide, and then a converged management so that you can actually manage this stuff. I hate the term single pane of glass because it's so overused. But really the idea is to try and get to some common way of managing your storage from HP so that you're not having to go to 12 different interfaces to manage it. And again, Lee is here. Haven't really introduced Lee yet. Lee is actually the product manager for our storage management products. He's going to come in this afternoon, and when we do that part about software defined, he'll talk you through kind of the strategic level of where we're going. And then you take those layers, and it's pretty amazing that what we said in 2010 really kind of fits to what everybody started to talk about. What is a software-defined data center? And it's this physical hardware layer, data services layer, and a control layer. And again, Dale will talk more through this, but this is the detail of how we're talking about this area. That there's software-defined storage, which is cost optimized. It's things like HP Store Virtual, being able to scale that up as a software product, and we'll talk more about Store Once now also being a VSA. I don't know if you guys saw that announcement, but Store Once now has a VSA. That fits in here. Then there's these things that we're calling SLA optimized or service refined storage. And again, I'm not going to try and talk you all through this. Dale will go through the details later, but that's where 3PAR would fit. And then there's the traditional, not optimized for a software-defined data center, kind of EVA, XP, MSA. Still traditional storage, still works, still does great in a traditional environment, but and then at this top layer is this management orchestration. And again, that's what Lee will talk about. Sam Feinberg, who's a distinguished technologist, is flying in now, and he'll walk you through some of the OpenStack integration that we have today and some of the work we're doing on OpenStack. He'll dive into that. So I am excited. So for me, I mean, it really is that we have a solid strategy and a great set of technology. Again, I kind of think about it over the years, and I stayed because it was a convenient place to be. I was making good money. I wanted to stay in Boise, but now I'm actually staying because I'm really excited. And there's actually part of this story that I almost forgot to tell you. There's a really important part of the story that I want to tell you. So last year at HP Discover, I was actually walking into Meg's keynote, and I got a phone call, and I didn't recognize the number, and me like a fool, I answer it. It's a friend of mine, and actually you know who he is, so I won't say his name. I'll tell you later. Who now works at EMC, calling me because HP had offered early retirement. Between my years of service and my age, I qualified by like 30 years to be able to retire. I think it was like, your years of service and your age, if they added up to like 60 or something, you could retire. Well, mine added up to 85 because I've been there so long, and not that old, but 50. So, and I could take retirement. I think I was something like 18 months is what I could have got to leave HP. Somebody from EMC called me and offered me a job to come work at EMC. I'm not going to take 18 months of salary from HP and leave because I think we've got a better strategy. I think I like where we're doing, and I'm not going to come work for EMC, even though I could walk away from HP with over 18 months of salary and start a job probably making more money at EMC. I said, nope.
And you like us.
Well, I would probably have worked to bring you guys to EMC events if I had done that, but I mean, there was just no chance I was going to do it. So, so I really am excited. I mean, this is not. I mean, I know I'm HP storage guy. I get probably a lot of people thinking that I'm just a pimp for HP storage, but I'm actually here, and I stayed here because I decided to stay, and because I'm really excited about the strategy and the vision that we have. So, anyway, well, I'm going to let the smart guys take over. I want to introduce Lemills. Lemills just walked in. Lemills actually works for the Americas, and Lemills, you manage major accounts or global accounts for the Americas. He was actually the 3PAR manager, product manager for the U.S. Still very involved in 3PAR. We'll let you. Actually, why don't we have you guys that are going to do the 3PAR section? Why don't you guys each introduce each other now, and I'll switch the slides, and PD, we'll just go around the room and you guys introduce each other so they know who's going to be talking to them.
Sure. Hi everybody, this is Priyadarshi. I go by PD. I'm the product manager for 3PAR. Take care of the hardware platform planning activities. Okay.
Good to see you again.
Yeah, good to see you.
I'm Siamak. One of the original HP software engineers. I stayed on with HP and I'm the chief software architect for HP 3PAR software.
Cool.
Welcome.
Mills Garrett, with HP.
I need to come up.
Jarrett. I've been with HP 17 years. Currently holding evangelist segment manager responsibility for our global accounts for storage across the U.S. and the Americas overall. Previous 3PAR product manager, previous product manager for the XP disk array, previous engineer on the XP disk array.
Previous engineer on NAS.
Previous engineer on NAS. Calvin was my marketing guy.
And he had dreadlocks back then, so it's just always funny for me to see him now. It's like, dude, what happened? You shaved up and you look like...
Started off doing magneto-optical jukebox firmware. That's my start of my...
So he's a really smart guy too. That's why I brought him. I tried to minimize the number of just pure marketing people here. So very few people that are pure marketing, and he's the guy that just comes to mind when I think of that.
Well, there's hope for him. I can stick with dreadlocks.
There you go.
Yeah.
And my name is Vish Mulchand. I run product management for primary storage. And as Kelvin stated, you know, I can run, but I can't hide. I've left HP 3 times, come back 3 times. Somehow or another, they've always been able to rope me back in. The most recent here from the 3PAR acquisition. So, you know, it's great to be back. I've been in HP, gosh, almost my entire career. I'm almost afraid to say when I started now. Been in HP from the days when Bill and Dave Packard were here at the company, right? So it's great to be back again, seeing many faces like Calvin, which I've known over the years. Just to level set a little bit on the session today, I'll be joined by Priyadarshi, as you guys met, as well as Siamak. Siamak gave a very modest introduction. He's probably the smartest person on 3PAR storage in HP today. Okay, so great that you guys have Siamak here, and we'll treat this as interactive as we like today. I know there's different levels of understanding in the room, so stop us. No question is a bad question. We can go to the board, we can go to the whiteboard, we can not do slides. You guys, it's your day, so you guys guide us, all right? Okay, good. So let's see. So what we're going to talk about today, primarily 3 topics. Flash optimized storage. I'll share with you sort of where Flash fits in the overall 3PAR offering. We'll talk about some interesting software releases, priority optimization, that's quality of service software. And we'll talk about peer persistence, which is the ability to do transparent failover, active transparent failover. Some people call this geo clusters, right? So hope you like the choice of names we picked for some of these products. It's always an interesting process to use to do naming. Any questions before I start?
Is there anything that we shouldn't talk about? I mean, just making sure there's no limitations.
Everything's open, especially since it's getting streamed, so anything you say is going live. So.
Cool.
Oh, is that right? It's all going streamed. Okay, very good.
You're live.
All right. Okay, there you go. I'm gonna stop the jokes then. You know.
Yeah, and just let me tell everybody this. So we actually have USB keys that have all the slides, but didn't want you looking ahead, so we're going to give it to you at the end of the day.
Okay. And if we do hit something that's confidential, or you know, we'll point it out, right? Again, because this is streaming live, I don't think we'll talk about anything futuristic or confidential, and you should be able to report on that. Okay. Okay, so meeting objectives. We want to first of all level set on our strategy. I'll talk about the overall 3PAR strategy and then the overall Flash strategy within that. And then we're going to deep dive on the 3PAR Flash optimized architecture. Siamak will spend a good couple hours this morning getting really deep. Flash is different, right? I think we need to recognize that Flash is different. Yet there's some things that are similar as well that people expect. So we'll be showing both the similarities and differences on how we deal with Flash.
Hey, Mitch, hold on just 1 second.
Flight tandem or what? With someone, or we done differently for Flash? We'll go through the 7450 product and how it compares to the competition. And then, you know, we'll also for sure cover customer use case and feedback in terms of how people are deploying some of these storage devices. Okay, so let's start here then. If you look at the converged storage vision that Calvin presented earlier on this morning, the HP primary storage vision, okay, is focused very much as part of the whole converged storage vision, right? And we are basically talking about one offering for primary storage, right? One offering across high, mid, low. One offering across block, object, file. One offering across spinning media, flash. this is in stark contrast to, I think, where the industry is heading, right? The concept is not new. The server groups have had this concept for years. The networking groups have had this concept for years, right? And why is storage so special? And this is exactly what you'll see us talk about as we go through the rest of the day today. Now, again, the focus today is going to be on the flash optimized piece, but keep this sort of context in mind here as we look at primary storage out the next 10 to 15 years, right? That vision. We've already been through this slide, so I won't spend too much time on it. But I think an important element of strategy is what you're not going to do, right? And clearly, we're not going to do something like this. We're not going to make a flash startup acquisition, for example, right? We're not going to go propagate different architectures. We're going to look to reduce them. Now, these are some more initiatives from a three-part perspective. Key initiatives to support our one vision.
Question, Rich.
Yes, sir.
When you say you will not be making any more acquisitions in that space, is that saying that in your roadmap going forward, right? You don't think there'll be any more revolutionary improvement innovations in that space that would require a re-architecting of your three-part architecture, or you just see incremental improvements in there that you can add to your existing architecture to make it work as well?
So that's a great question, right? So the question I guess is, do we not see any revolutionary changes that will force us and start from scratch all over again, right? So I think that revolution, the possibility of the revolution always exists, right? So far, our approach has been to isolate media transitions from storage transitions, right? So whether you're using nearline media, whether you're using flash media, whether you're using memristor media, we want to be able to say, hey, great, how do we isolate that from you? Now, I think if you look from a customer perspective, customers would always prefer an evolutionary or incremental approach, right? Because it's easier. I think the industry history has shown us that evolutionary approaches work every 10 or so years, and by about 15 years or so, something new comes along that forces a revolution, right? So to answer your question, I believe, there's always that possibility, and where we can extend technologies, right, or isolate them down so the revolutions are not so wide sweeping, and that'll be the approach, right? And I liken that to when the x86 industry first sort of took off, developing technologies at that early stage and developing it now. I think anyone in their right mind today would be crazy if they built a new server architecture without x86 compatibility, for example, right? So that notion of revolution and evolution, I think, is going to be very, very intertwined as we go over time because of the investments people have made. Other perspectives?
Along those same lines, I mean, HP among a lot of other companies seem to be investing a lot in ARM these days, as far as a server architecture to use.
Yes.
Now, obviously, is not compatible with the
x86
architecture as well. So
I think that's another interesting one, right? Where how do you bridge revolutionary transitions like that, right?
Yeah.
And I think ARM and those mobile level processors bring yet another level of change to the server industry, right? You got to bridge that gap, right?
Yeah.
That itself is a revolutionary change.
Yeah, exactly.
Brings about a new revolution to what you can do from a computing point of view.
Well, Flash is a revolutionary change, if you ask me,
Exactly.
right? And you just as you think Flash is revolutionary, there's going to be a Flash 2.0, which would be even more revolutionary, I think. And so the question becomes, as you get revolutionary media, how do you isolate from the other aspects of the storage control? That to me is going to be the approach we'll take. Okay? So if we look at these sort of initiatives, you can see Flash sort of here in the middle as a very key focus area that we'll be covering. Now, I won't go through this entire list, but let me walk through a couple of them at least, right? When we got acquired into HP, I think the first thing that the three-part team was asked to do was to go refresh the mid-range platform. HP was the leader in the mid-range storage platform. It lost ground over several years, right? And so the first thing they said was, okay, guys, we need you to help us gain the ground back there. And with the StoreServ 7000, okay, we accomplished this first objective. At least we got our product out to that end, right? I think it's going to be a multi-year journey where we brought a next generation mid-range platform, and we brought tier 1 capabilities into the mid-range, right? Things like the ability to have more than 2 controllers, the ability to survive a controller failure gracefully, a priority optimization software, things that people expect in higher end systems, right? The ability to do online upgrades without depending on multi-pathing, like NPIV. So that was one of the key focus areas. You're going to see us now in the next release focus on a lot of tier 1 capabilities. Some of these software capabilities like priority optimization and persistent ports, we did announce together with the mid-range product. We also in June announced our first 7450 all-flash array, right? So you can sort of see where flash fits. Now, what do we have coming down the road? Converged file block object. Running file block object protocols native on a controller. Not hiding 2 separate pieces of hardware in there, right? Again, I think there's going to be a segment of the market that wants that. There's going to be a segment of the market that will want dedicated infrastructure, right? So I think, again, we'll try and cover that. Virtualization, server virtualization, right? Storage for server virtualization. I think the dirty little secret that most people now know that the success of any server virtualization project is highly dependent on its storage. And I think the industry forgot about that early on when they started, right? And I think this has been a strong area for 3PAR. We'll continue to focus in that area. There are things that I can't talk about that are coming up in the future now in this room, but I'm sure you guys are tracking future developments with VMware, with Microsoft Hyper-V, with KVM, okay? We're going to be actively in all of those future developments focused there. Storage federation. The word federation, from my perspective, means treating a pool of storage devices as a single logical whole, right? And you want to be able to do things like provisioning, load balancing, asset refresh, high availability in a federated model, right? And we don't believe that federation should be hierarchical as it is today in some implementations. We believe, just like in the server industry, that a federation needs to be peer-based and not hierarchical-based. And this topic, we can spend a whole day as well drilling down into more detail. Yes, Ray?
So you're not talking storage virtualization per se, where...
Yes, we're not talking storage virtualization per se. Okay, IBM SVC, EMC vPlex.
HDS.
Yeah, yeah. So we would be bold and contend that architecturally that is not the way to go. Okay, because of the following reasons. Number one, storage virtualization, external storage virtualization adds another layer to your storage infrastructure. It adds cost, it adds complexity, it adds risk. And here's the thing that always gets me to this, right? You've got intelligent storage, then you have an intelligent layer above it with a switch. Why put intelligence in 2 layers? If you had dumb storage and intelligent switch, I can see how that model works. But intelligence and intelligence, it seems like overkill to me. And again, if we go back to our brothers in the server land, which we seem to follow quite a bit, it's peer-based in the server land, right? Why is it so special again with storage? And I can tell you what the reason is, right? Many of the storage architectures were designed 25, 30 years ago. Storage virtualization hides that complexity. It doesn't solve the complexity problem, right? It's like sweeping the dust under the rug. And my contention is, go solve the complexity. That's what's going to take you for the next 10 to 15 years moving forward. Okay? So I think, again, we can deep dive. This is a very interesting topic. Maybe, Calvin, one of the things we can do as a follow-on is come back and talk about federation. I think it's going to be a very interesting 10-year journey. And then, of course, this notion of capacity efficiency, I think now more so than ever, with the data explosion, with the price of flash, is more important. Thin provisioning being one of the technologies for capacity efficiency, deduplication, compression, these are key pieces. And I'm going to be talking about deduplication for primary storage as well, right? That's another very interesting topic and debate. Okay, questions before I dive down into flash. Ray?
So Vish, you see the file service coming out of Windows Server, like it is integrating that into the 3-power controller?
So today we have multiple offerings in that space, right? We have a Windows file server gateway product, right? That's Microsoft Storage Server, and it does very well for things like SMB performance. And then we also have something called HP Store All, which some of you may be familiar with the iBricks technology that we acquired, right? Moving forward, our native product, 3-power file controller product, will bring technologies from multiple places. Okay, there'll be components of iBricks, there'll be components of a file system that we'll talk about. There are components of technologies from HP Labs, right? Again, there'll be several components that we bring together to provide native file services.
Executing inside the 3-power controller.
Executing inside the 3-power controller.
The object services will come from where?
The object services?
Yeah.
Okay, object services on the controller as well, on the software end. Okay, now again, I don't think this is a model that you would deploy for large-scale object deployments, right? I think you'll have a slightly different approach for large-scale deployments. One sort of area that we can think about and talk about is this notion of capacity-optimized storage versus performance-optimized storage. What happens when, if you believe that the object protocols are going to take over the world, where you then want a very smart object indexing layer, and then the ability to store deep and cheap? I think that's another interesting area. I don't know if Siamak, if you want to add to that piece there, from your perspective.
I think it just depends on the nature of the use case, right? There are use cases that are random access database models, and there are use cases that are whole file model, right? And those things are going to continue to coexist, right? In the whole file model, where that's your primary use case, an array such as ours may be a little too expensive, but there are use cases where the objects are important and you actually want to store it on the array itself, right? Because availability matters. Those are the two use cases, and we actually sort of keep two different platforms for those who use them.
And the asynchronous streaming replication, what does that constitute? I mean, you have synchronous replication today.
So the asynchronous streaming replication will get you to asynchronous replication within a 30-second window, okay, or less than a 30-second
Rather
window.
than an hour or
Rather than a
schedule
5-minute
sometime,
window
yeah.
or 10-minute window, right? Which is more snapshot based, right? And again, today async replication in that narrow window, HTS offers it, EMC offers it at the very high end, right? HP offers it on both the high end. Now I don't remember if did EVA offer. EVA offered it, and we'll bring this down as well down to the mid range, right?
And persistent ports?
Persistent ports is the ability to do a online upgrade without depending on multipath. It is implemented get a port take on a virtual guest identity. Right? It also allows you to do things like planned downtime, planned upgrades on your controllers, and our next release here will be able to also sense when you lose a cable to that port. Okay? Other questions?
Unplanned also, right? If controller fails.
If a controller fails, yeah.
Today we will automatically migrate the both personalities so that the transition takes place at a fiber channel level. The SCSI layer never figures out that this is all happening, right? It was much more seamless.
So to clarify, that is for the FC ports only.
For the FC ports only at this point in time.
FC
On
and
iSCSI.
FCOE, yes.
Okay.
Yes. Okay. Do you see a need for this in iSCSI?
Just for
Consistency.
consistency at least, yeah.
Okay.
Is there any intent to go beyond 8 controllers?
Another great question. So, there are two kinds of things, right? There's technical things and there's business things. So the ability to go past 8 controllers technically, absolutely is easy to do. I won't say easy to do, it's possible to do. Okay, we have the technology to do, it's not easy to do, right? But here's the question. If you have a federation strategy, should you federate a bank of 8 controller systems? Or do you go 16, 32, 64? Right? I think we could do, just like if you go back to SMP on the servers, we could get up to 64 controllers. The technology that we have in place allows us to do that. The question is, do we think the industry is going to head out that way? Our bet is that it's going to be federation of these medium-sized controllers, right? 8 controllers or so, federate out. I don't think we'll go to 64-way, 64 controller-capable storage arrays.
Part of it is also you have to think of it, what is an administrative domain, and what sort of firmware upgrade story do you have, or change management story do they have, right? So typically change management or firmware upgrade applies to the entire array, right? So now if the boundaries of the array goes up to, say, 16 controllers, right, and you've got 4,000 drives behind it, and potentially 5,000 hosts in front of it, right? Just any sort of change management requires a nightmarish sort of coordination effort with a whole lot of stakeholders, right? So So if the model is that you have sort of this change management for something that is reasonable size, and then you have, using federation, you make your storage pool much larger in a much more seamless way, but the change management applies to individual element, it becomes a much more palatable story.
Yeah, the federated environment is a LUN span multiple, I'll call it controllers.
The LUN will never span multiple arrays,
Right.
but a LUN, the best way to think about a given application will always reside in a given array. But you're able to migrate the load.
I hate to stop you, but my
One
microphone is very clear.
So-
I mean,
so-
we're having some sound difficulties.
That's okay. The best way to think about the federated model is that a given application is deployed onto the federated system, but it's actually hosted in a given array at any given time. And based on load characteristics, based on administrative will in terms of what they want to do with load or a new array showing up, the application may migrate from one array to the other array. So when you say an array is about to come offline, you press a button, it gets vacated, the application will move away. The brand new array shows up onto the environment, you press a button, it sort of discovers, what's the most loaded and moves on applications onto the new array. So that's the best way to think about it. But for change management reasons and failure bound reasons, you don't really want a given LUN to be split across multiple arrays.
Latency effects as well, right?
Latency, we can work around the latency because at the end of the day, we are sort of are able to do migration. During the migration, the LUN exists in two places, but at least in one place, it's always whole. It's really around failure management, right? If something, let's say power goes out, what do you do with an array? One array loses power, but the other doesn't lose power. What do you do with these kind of weird, thorny situations? And that's why we would like to have a complete picture always in one place, right?
Okay, other questions? Okay, well, let's keep going then. So let's talk about sort of the approach to Flash and sort of HP's enterprise group solid state strategy, right? So clearly, we want to optimize for solid state arrays. Flash has differences from spinning media. We'll show what those differences are and how we've optimized it around multiple dimensions. Performance, there's both IOPS, there's latency, it's also bandwidth, right? We're doing that many IOPS with that many, that high rate of IOPS, your bandwidth can be limited if you don't watch that carefully. Density, how much capacity can you pack in a single view? How much performance can you pack in a single view? And then form factor, right? Is this going to be in a dry form factor? Is it going to be in a PCI card form factor? I think there's a whole variety of different pros and cons to go look at, right? So clearly this focus on optimize for solid state arrays. The next two are going to be areas where we differentiate from the rest of the pack, we believe. So in our mind, this game on Flash is all about software. The hardware is very, very, very exciting, but everybody does the hardware, right? And everybody can do the hardware. I think the ability to bring data services, right? The ability to do things like priority optimization, replication, snapshots, compression, deduplication, tin efficiency. That, I think, is going to be how people maximize the ability to move data. If you had data in an all-flash tier, can you move that to a mixed array? Or to a cold array as time moves on with your data? So this notion of data mobility, I think, is going to be very key. Service and storage. So at the end of the day, you're trying to deliver a service level to an application. All right? And you want to make sure that you bring the best possible infrastructure to serving that application. Whether it's flash caching on the storage array or on the server, collaboration of some sort, whether it's some mix of software-defined storage. I think there are lots of interesting things here. When Dale comes to this afternoon, we'll talk about the confluence of fast processors and servers, fast solid-state drives, and virtual SAN software. That brings a very interesting combination. Makes things capable now that were not possible several years ago. Solid state is a tier in service and storage. We've been doing this now for, 3 to 4 years, together with sub-LUN tiering technologies. And I can tell you that today, we just did a flash survey in the install base. 65% of our flash customers are using tiering in some form or fashion. If you're running a large number of applications on shared storage, I'll contend that tiering is still the most cost-effective way to deploy flash, because on a large number of applications on a shared array, you'll find that a small portion of that workload becomes hot, a a larger portion of that is cold. Well, that changes over time, right? And so the theory is you want to be able to move what's hot into flash. Now, having said that, it doesn't mean that all flash arrays don't have a play, but they do. And the all flash arrays, I think, are targeted at much smaller databases. Maybe not as many applications being shared, but intense need for latency, intense need for IOPS.
I had a question on the all flash stuff. One of the things I saw on the 7450 when it came out was it was SSD only. Is there anything from a technological standpoint that restricts it to SSD only? I mean, I would think there would be customers out there that would want to be able to have a mixed tier environment on those more powerful controllers with more cache and faster processors. And
Yeah. So the question is, the 7450 is launched as an all-flash array. Can we put spinning media on it? So that's an interesting question because I think some of the early startup vendors or some of the early vendors on flash were portraying a perception that traditional storage with spinning media, if you have any spinning media on your flash array, you're not really a, no pun intended here, you're not a pure device, right?
I see what you did there.
And so, I think when we brought the array, technologically, I think we can absolutely put spinning media into that array. I think there are considerations as to why you would do that and what you do with that handling. I just think that there was too much of a perception of what people are termed flash washing. Or your traditional array, you put some flash drives in there, and now you call yourself a flash array. Well, that doesn't cut it, right? So I think the industry as a whole will get there, Nate.
Yeah.
I think today the state of evolution is people are expecting all flash arrays to be all flash. Okay, so again, we have the possibilities of doing that.
Yeah.
It's a question of how the industry adopts it. Yeah. Okay, so tier, and then the next one is next generation flash technologies, right? So today the issues with flash involve a couple of things. Number one, the read-write performance ratios are different. There's also a endurance factor in today's flash technology, right? Depending on how the drives have been over-provisioned with the cells. And so the next generation flash technologies now solve the read-write performance issues, and they solve the write endurance issues, right? And now, I think the notion of non-volatile RAM comes into play. I think this is a very exciting phase because what does this mean? Does this mean the end of storage? Does this mean the end of memory? I don't know. Does storage become now byte addressable as opposed to block addressable? Right? And you talk about bringing a service level to an application. I think in this era here, if you look out the next 3 to 4 years, I think we see some very interesting disruptions, revolutions, right, to the programming and application programming model, right, with this kind of capability. So I think watch the space. It's very exciting as well. So there are technologies in HP Labs today that are already looking at this. As we develop next generation storage arrays, we are also looking at the ability to make sure we can accommodate this kinds of media. And I think again it brings a whole new dimension to where the world is heading for the next 4 to 5 years.
Besides the
Questions?
endurance, and you think it's going to speed up the access and latency as well? Besides the reliability and the endurance, you think there's going to be a dramatic change?
Yeah.
Latencies are down to like 0.2 milliseconds, 0.3 milliseconds
Yeah,
today.
I think we'll
There's
get
not much
down.
left that we can actually measure.
Yeah, I know. Laws of physics will catch up with you at some point in time, right? But I think today we're talking 200-300 microseconds, maybe 400 microseconds. I think we'll get down to below 100 microseconds, maybe even below 10. I don't know. Siamak, what do you think?
Right now, the thing that dominates the latency is the distance to the array itself, right? Both in terms of protocol stacks, the firmware that you have to sort of traverse through to get there, right? The question is, can we flatten some of that distance, right?
Like putting it in the
5%,
server,
for
like
instance. Well, you could do it 2 ways. I mean, there are some advantages to having shared storage. I mean, if you put it inside the physical server, if the server fails, all of a sudden your application is down, and guess what? You're waiting for the CPU to come before you get the application out. And that's untenable for a lot of applications, right? You have to have shared storage, externally accessible, so that a physical failure of a CPU doesn't take you down, and you're able to actually fail over. So external arrays will continue to exist, and there's a reason for them to exist, right? And so now the question is, how do you actually deal with the protocol latency and drop the fiber channel from the mix? And the question is, do you go to some sort of PCI Express fabric? Do you go to something like InfiniBand fabric, right, where they have demonstrated lower latency because the protocol stack is a little thinner, right?
Yeah.
So that's really what we're looking at, both for back end So for us to talk to the storage and to the front end, for us to talk to the actually storage devices, to the host that we are providing services to.
Other questions on the strategies, flash strategy? What I'm going to do now, if there are no questions, is maybe dive down into a little bit more detail. Let me just flash the product line once again so you get some context and perspective. Here you can see on the chart is the 3PAR product family. On the left, or on your right, the left, we have the 7000 series. This was introduced back in the December timeframe. And this is a revolutionary product. It's doing really well in the market because it's got a brand new sort of view of high-end capabilities into the mid-range. On the extreme right is our 10,000 series. This is our workhorse, where several large service providers are running this array. And then here you can see the 7450 sort of fitting in the middle of the product line moving forward. Right, so that's the family where value, performance, and scale matters. One key point here to note again is one operating system, one architecture, one set of common data services. This is the largest benefit that customers resonate with in terms of the software.
That's why I'm excited.
Yeah, it's great. I mean, again, like I said, not a new concept, right? And you know, talk about extending it in either direction, right? Up and down, right? It's just great way of moving forward in my mind. And then if you can federate across this offering, think about the possibilities it brings: replication, data mobility. All right, the 7450, a quick product introduction, and then I'll hand it over to Siamak to drive down into the details. You have essentially a 7450 comes with a 2-node or a 4-node configuration. You can see the performance, number of IOPS. This is a 4K random, 100% read, and latency. All right, you know, we've made the point to talk about IOPS, latency, block size. All right, so I've talked about all three. Otherwise, you get lies, damn lies, and statistics. People have talked about IOPS at 30 milliseconds of latency, right? Irrelevant from my perspective in Flash. So again, you can see the data points. Also, you can see the bandwidth, right? Oh, sorry, it's a typo.
It's not 5 million.
There you go. Hey, that's good, man. See,
Wow,
that's a good
5.5 million IOPS.
5 million IOPS.
The more you talk about it, the better it gets.
That's pure SSD right there now. So, all right, the cache sizes. You can see what we've done on the 7450 is we've actually doubled the size of the cache versus the 7400. If you go back to the family slide here, right? We've actually doubled the cache, and we've also made a faster controller, higher number of cores, higher frequency. So there are hardware differences. We'll support 3 different types of drives today: 100 gig, 200 gig, and 400 gig MLC. We will continue to add additional drive types. We also support an encrypted 400 gig MLC drive. I'm surprised already to hear a couple of companies in the healthcare industry want to get those encrypted drives, all flash. Okay. We also have a customer running OpenVMS, all flash. So, okay. That's good. You can see
Or OpenVMS people.
lots of financial customers using that, you know, and you can see in terms of the capacities what it supports. Now, this is an interesting point here because clearly the number of SSDs exceed the controller performance that the array is capable of supporting, right? And we had to learn the hard way that customers said, look, I want to be able to lay out my capacity. At any one point in time, a portion of that capacity would be hard, right? But don't limit my ability to lay out capacity just because your controller is, you know, not saturated, right? Go beyond that. So I think you can see here we offer the ability to go up some decent capacity. And as we bring bigger drives, 800 gig MLC, 1.6 terabyte, 2 terabyte, that capacity goes up. Okay? Quick introduction on 7450. Any questions before I bring on Siamak to drill down?
Logistically, how long do you think is Siamak going to be like presenting now for a while?
Yes, Siamak will present for the next. If you like 3 days, we can do that too.
Do you want to mic him up, Jeffrey? Jeffrey, you want to mic Siamak up? He's going to be presenting for a while. Or you want to just go ahead and use the mic where it is?
Let's continue on.
Okay.
You want to mic up Siamak? Or?
Yeah, no, it's going to take too long. So let's just.
Okay, Siamak, I'll hand it over to you to.
Few people watching are complaining when you're typing, but it's like, they're going to type. I'm not going to tell anybody not to type. So if you guys want to pound harder on your keys, and maybe we can do a song together for everybody watching.
That could be the orchestra meister.
When you wish upon a star or something.
So, just as an introduction, I tend to speak really fast, so please just slow me down and ask questions as we go along.
What was that again?
Anyway, I'm going to talk about essentially what features were needed for SSDs, what features we brought on from the previous generation of the architecture itself, and sort of what we had to do to the architecture to accommodate SSDs, right? And this is sort of the performance that we are actually seeing from the new line of products that we produced. And so the nice thing about this model is that this graph shows, you look at the 7450 versus, you look at the 7450 versus 7400.
I can't hear on this here.
Them up and look underneath. All you see is a couple of extra cores and a little more memory. And software-wise, they're on the exact same piece of software. So the additional enhancements that we did, but the same software essentially runs at both, right? This really tells you something about the software architecture itself. This really says something about the fact that it's able to actually scale without locks when you have 8 cores in 4 different controllers.
Siamak, are those all,
Sure.
all SSD configurations?
These are all SSD configurations, correct. So we put essentially as many SSDs in 7200, 7400, and 7450 as was needed to sort of max out the CPU.
And those are all -4 configurations, or
Dash
4 controller?
7200 is obviously 2 node. 7400 is a 4 node. 7450 is also a 4 node controller. Right. So the point I'm trying to get across from this graph is essentially the capability, and this is the service time running at 500 microseconds. The point of this graph is that we are able to actually get to the numbers, right, at 500,000 IOPS. It's actually can go beyond 500,000 IOPS. At 550, we start to saturate the CPUs. Then the software is designed to actually be able to actually use all the cores in the system. And if there were more cores at our disposal, we could actually take this graph further to the right. And I'll talk about.
And that's the place you want to be, right? You want to be
Right.
compute bound, right?
Exactly.
So when we get onto the
Right.
details.
So along with the question, how come you guys use 8-core CPUs instead of a 10-core?
It's a matter of cooling, right?
Cooling,
I mean, at
okay.
some point in time, you just run out of juice and cooling capacity inside, right?
Okay.
Now, we also ran into a situation where we wanted to go to Ivy Bridge CPUs with 10 cores, and for scheduling reasons, we had to actually go with 8-core Sandy Bridge.
Okay.
The board itself is Ivy Bridge capable. We actually made the changes to make it.
Oh,
So
okay.
that's one change that is within 7400 and 7450.
Okay.
The board has been relayed out to actually do Ivy Bridge support, but we just ran out of time in terms of commitment
Okay.
from Intel. So, in terms of where we are, these are now offerings from other vendors with SSDs. Okay, so one note to pay attention to: these are actually using, at least the NetApp uses very similar CPUs to our blocks. Okay, they're not using particularly worse CPUs than what we are using here, but the software is allowing you to have a much flatter line in terms of both latency and in terms of the IOPS as it's going to the right. So these are the various companies that have had SSD offerings added to their blocks, right? And if you sort of open them up and look inside, there's very similar CPUs, yet the software stack is really running out of juice, right? They really aren't able to scale as much as they should.
Yeah, I think there's another interesting part of this slide is that if you look at the use cases, right, there's an all-flash array use case, but there's also a traditional mid-range array. Move on to the front. There's also a traditional mid-range array and the use of sort of all-flash configurations, right? So I had a customer come up to me and says, I don't need 500,000 IOPS, I need 110. I said, okay, great, run around 7200, right? So I think that's going to be a use case where some of these mid-range platforms have an all-flash config, and you can see this chart was probably focused on looking at that mid-range sort of mixed-use model, right? We'll come back with another 7450 SPC1 to show an all-flash comparison, but this is interesting to see the other models like the IBM and the HUS from Hitachi.
And because we've been talking about solid state, I just want to make sure we understand that this is not the solid state array. This is just our everyday 7400 array, not our solid state array.
And the F400 is obviously not a solid state array.
That's right, exactly. And there for historical perspective, right? For people that run F classes like yourself, Nate,
Yeah.
they can show you sort of the generational improvement, right? And I think the important point is as well, publishing an SPC1 benchmark, right? This is a different workload from the prior 100% random read. And again, it's in my mind multiple data points, this being one of them.
I'm curious, because we're talking about SPC1, how come 3PAR and HP has yet to publish any SPC2?
Stay tuned.
Okay, cool.
Publish.
SPC2, it's a sequential workload.
It's much more bandwidth as opposed to IOPS.
There are not a lot of all SSD arrays that publish SP2.
Just in general, in the history of 3PAR, they have yet to publish
Any,
SPC2.
for
Yeah.
anything,
Yeah.
yeah.
Okay, yeah.
But stay tuned.
Okay.
So, what does Flash do? I mean, so this in terms of comparison, right? The nice thing, the best way to this is a good chart to sort of describe what the differences are between the two, right? The latencies are milliseconds versus microseconds, right? I mean, it's not atypical to actually send a command to a drive between the seek time and the head seek time and the rotation seek time to actually get something back in 10 milliseconds, right? And really, if you're pushing it, hundreds of milliseconds is easily observed on drives. Beyond it, it's also very uneven access times, right? Versus microseconds on the flash media. And the part that is kind of interesting, and when we started 3PAR, the typical size of a drive was I think the first drive we shipped was 76 gigabyte in size. Out of the 76 gigabyte drive, we were getting about 100 to 200 IOPS. Today, we ship drives that are 200 terabyte in size, and we are still getting about 200 IOPS out of those. So if you look at IOP density of the drives, they have gotten significantly worse. So if somebody sort of draws a graph of what the CPUs are doing in terms of performance, it keeps going up. If you drive, a graph for the drives, the performance keeps going down, right? It's still the same 200 IOPS, but over a 2 terabyte capacity, right? So it's like 100 times slower than it used to be, right? And in terms of when the customers are buying, they often buy for capacity, and sometimes they don't think about the IOP implications, right? So this is actually completely changing the game, right? For the first time, storage actually becomes at silicon speed. So it actually picks up, it fundamentally changes the curve in terms of what the performance would look like. So that's something that is really, really interesting. So the 0.2 IOPS per gigabyte becomes 100 IOPS per gigabyte, right? That's over 500 times as fast, right? So you actually go back on the silicon curve in terms of the performance. But of course, you have to worry about the performance, the cost, right? It's 500 times faster, but it's 10 times more expensive, and it's something that people have to get their head around, that it is going to be fundamentally more expensive. But there's a second piece. You can deal with this flash media expensiveness because you can sort of say, well, I'll use sublun tiering, or I pick my applications that are important and I just put it on there. So you can sort of manage that by application. The thing that is much harder to deal with is the cycle rights. And if anything, that's actually getting worse, and that's the part that you have to worry about. So if you think about the current generation of 26 micron feature sizes, they get about 15,000 write cycles before the cell dies. At 22 feature size, at 5,000 they start to die. So all of a sudden it's actually getting worse. So now you have to worry about the flash life, something that you didn't have to worry about on the drives. I mean, they had mechanical failures, but you didn't have to worry about the wear. So there's a new type of failure that you didn't have to deal with. Now you have to sort of think about that and manage that actively, right? So what do we do to step back and actually fix up our code to deal with SSD? So it was all about performance, the fact that these things are much, much faster. They have implications in cache management, but you also have implications around wear leveling. And so these are some of the technologies that we've developed over time. For the 7450 specifically, but it's a software, so it applies to 7400, 7200. So whomever applies the latest update actually picks up these features automatically, right? One is adaptive read, and that's around the fact that you can actually do a different algorithm. In the past, you wanted to hold on to the read cache as much as you could, okay? With the SSDs, you don't really have to do that, okay? And you wanted to read as much as you wanted from the drive, because going to the drive is so expensive that if the customer wanted to do a 4K read, you did a bigger read from the spinning media, right? But the SSDs are the other way around. It's so fast to go there, you don't really want to pollute your cache with too much stuff from the SSD because it's relatively cheap to get to the drive itself. And we'll talk about the details of that in a minute. And then we have adaptive write. The idea behind adaptive write is that in a world when you have to, at the end of the day, you have to send the data out to the drive. I mean, that's kind of the whole point. But you're holding out to the cache as much as you can. So now you actually change it so that you don't send repeated rewritten data to the SSDs to manage the bare level. We'll talk about the algorithms involved so that we actually preserve the life by not doing excessive writes to the flash. And a lot of it is around the flash the flush management and cache management inside the box. We also have what we call autonomic cache offload, right? The idea is that you have to carefully look at the cache for the RAID 5. I mean, often people set out RAID 5s, and there's a big difference between sending read modified writes to the RAID 5 versus full stack writes to the drives. And we'll talk about what we do to ensure as many full stack writes as possible, so we actually again preserve the life of those SSD media. There's also the idea of multi-tenant I/O processing. This is the part that you have to be careful about versus read versus write. The SSD drives have this property that if you're actually pushing too much write load on them, they actually start to impact the read performance on those. So you have to be very careful about sending multiple reads and multiple writes to those drives. And beyond it, you also have to do, at this point, it's all about the IOPS to the drive. So if you have multiple applications, and essentially they can have many, many thousands of IOPS, if you have sort of unconstrained the CPUs, right, you have to manage the application workloads, right, to make sure the given application doesn't monopolize the entire box. And so this is around quality of service optimization. So there's a lot of services that goes into managing cache, right? The second piece is, well, we always had the 3-part ASIC. It's always been there. It's the same ASIC as we've had before. But it turns out that the spinning media really didn't force or push the ASIC too much.
Yeah,
so there was a series of enhancements in the ASIC that we never turned on, right? Because it was just not justified when you were using spinning media. So when you step back and say, okay, now all of a sudden the game is around latency, right? One extra interrupt that is required for I/O processing, that adds to the latency that we were talking about, right? One extra interrupt adds about 20 microseconds. If you could eliminate that, you actually gain a 20 microsecond latency improvement right then and there. So it turns out because ASIC had this remote DMA capability that we never used, by turning it on, we actually all of a sudden got a 20% improvement in latency and about a 15% improvement in throughput, right? So that's
So is that sort of is that sort of headroom built into your ASICs where you can sort of future-proofing, if you want to call it that?
Yeah, I mean, often what happens is that when you put out a new ASIC, right, it has a lot. I mean, we sit down and talk to the ASIC folks, and we design the ASIC for a 5-year lifespan, right? But the first instantiation of the system with that ASIC comes out in 3 years, right? But the software doesn't exploit all the features, right? But we built a lot more features with the anticipation that the software will turn them on over time, right? I mean, think about Intel puts out a new CPU and has some fancy instructions, right? And now you get Windows 2008 and install one. It doesn't use those instructions right then and there, right? But the next version of Windows 2012 all of a sudden starts to use those fancy instructions to do something interesting, right? Think of the ASIC as having the exact same property, right? It has a lot of fancy instructions that the first get-go of the software doesn't actually use them, but the first generation of software on the exact same hardware will just enable those features, right?
Thank you.
So we actually had to work on the controller scalability, and we'll talk about some of that. But some of these actually kind of existed beforehand, right? So the way to think about the 3-part architecture, and we'll get to that in detail in a little more. We start as a server operating system as opposed to sort of an embedded storage operating system, right? I mean, all the folks that came to 3-part came from Sun, where they worked on Solaris, and they worked on sort of big multi-threaded 64-core CPU machines, right? So they had very much a server operating system model in their mind, right? So if you look at the number of threads, the number of cores, the way we actually do white striping, all of that was designed from the beginning into the box. So we'll talk about the details of why controller scalability and system-wide striping matter. In terms of cache, you brought up the question of, is the LUN striped across 2 physical arrays? They're not. But internal to the controller, and this is unusual for us, nobody else does this, a given LUN is actually striped across all the controllers, right? So everybody else, if you look at the others, they have to carefully manage their LUNs. A given LUN is managed by a given controller. So what they do, they force people to actually make a bunch of tiny little LUNs, and that's how they get their white striping at the host level, because they take a bunch of LUNs and then use some sort of device manager or volume manager and put them together, right? On ours, you can make a big LUN. The LUN is internally chopped up in tiny little groups
that is actually inside the box and is actually white striped across all the machines and controllers and CPUs, right? A very different design. And then we add quality of service to actually get going. There's a whole bunch of other technologies we had to do, we already had, 3/4 thin. This is the case of detecting zeros and not writing them, right? That's always been there because we have the ASIC. So that gets you some of the way there. We actually have a wear gauge now that looks at the actual, the amount of writing that you've done to the drive, so you can display it, alert it, and so on, right? And we actually have some, and the nice thing about this data all comes back to 3-bar, to HP. We carefully look at the actual wear gauge on the systems that are out there. Right now, the most wear we've seen on a drive is about 95%, and this is on drives that have been out there for more than a year. So I think we actually have a good sense of historical data, so we can manage these both in terms of software management, in terms of active customer management, to make sure that they don't run out of the drives don't fail on them. And then you have this notion of system-wide strapping and sparing, and that actually turns out that we did this for performance reasons, but it turns out to be a perfect fit for SSDs, right? So in a traditional environment, you have a drive that is set aside as the hot spare, right? So that means that the other drives get a lot of writes. We don't have this notion. We have spares set aside from each one of the drives, so which means that you get much more, even wear across all the drives in the system, not as opposed to within the drive itself. And we can talk about that in detail when we get there. And then we also talk about step size optimization. We have slides on that too.
Yeah.
So we'll talk about the step size optimization. So
I have a question.
Sure.
Going back to the wide striping and the wear gauge stuff, would that, with RAID and writing, would that not increase the chances of having two drives fail at the same time because they're both being worn at the same period of time? And what's the policy around perhaps proactively detecting when the drives are getting close to the end of life?
That's a very good question. So the way we manage the reason we have the wear gauge is to be able to actively manage it. So when you get to about 5%, when you get about 10%, we actually start to warn the customer that this is about to wear out.
Okay.
At a 5%, we actively start to actually manage the drive by vacating the drive, and to make sure that the drive never gets into a point where you're no longer able to write to the drive.
I'm curious from a stats, because you guys are pulling up all the stats through all of your customers. Do you find that on customers on their SSDs as a whole, is the wear spread out among all of them? So for example, if the customer has 24 SSDs in their array, will they have to replace all 24 SSDs in a very short period of time?
Yeah, so that's a very good question. So the fact is that people don't buy all the SSDs in one shot. People tend to go through upgrade cycles, right? So because of the upgrade cycles, and because they sort of buy it every quarter, every year, or whatever, if you look at the lifespan of an array, which is around 5 years, right? It isn't the case that they bought all drives at the beginning of time, especially because of thin provisioning, right? People do over-provision and they add storage as they go, right? Mm-hmm. So we actually see this sort of stepwise wear happening on the box itself, right? So it isn't quite as bad as it is as you described, that all 24 die at the same time. That's one contributing factor. The second contributing factor is that as you add new drive, we actively manage it so that you start to actually reduce the wear on the older drives.
Okay.
Because we load some of the IOPS to the newer drives.
Yeah. Okay.
Okay. So let's talk about sort of adaptive read in terms of the cache. It turns out that if this wasn't a flash device, right, and it was a spinning media, if the read came from the host, let's say it's a 4K, 2K read, when you go to the actual spinning media, it's so expensive to go to spinning media that you want to bring a bigger chunk. We happen to pick 16K as the chunk that we bring in. That's the size of our cache line, right? So you would always bring in 16K. So in the anticipation that the next read from the host, let's say another 4K, is right next to it, it's actually sitting already in cache. So let's assume it's doing 4K at a time reads, right? But it's all sequential. But by bringing in 16K, the next 3 reads are also satisfied from the cache line and doesn't require going to the disk, right? It's a great optimization. It turns out that for flash, that is not such a great optimization, right? Because these drives have such fantastic IOPS that if you actually use the 16K, you're actually could run out of bandwidth on the flash itself, both in terms of the SAS and in terms of the media itself. So if the 4K is really just a random 4K, having brought a 16K has depleted your bandwidth to the flash media itself, right? So what you really want to do is just bring in the 4K, right? That is the actual amount of data. It's a little over 4K because of diff, right? But you really just want to bring in the cache line that is being asked by the host. Now, this does not take away our sequential optimization. In other words, if we detect that the actual I/O pattern from the host is sequential, right? And we actually have, software in there that detects sequential access from the host. And not only that, it actually can detect up to 4 independent sequential reads in the same volume. Imagine that you have a database that is hitting the exact same volume, and there are 4 queries going on at the same time. There will be 4 sequential accesses, right? Even though they're interspersed, we're able to actually sort of desegregate those two and figure out that there's 4 sequential accesses going on at the same time. In that case, then we're actually bringing in 16K to stay ahead of the actual reads from the host, right? But in the case of the random, which is a lot of cases with the flash I/O, then we're actually sticking to the size of the I/O that's coming in from the host, right? And that's really just around bandwidth management. And it also helps with the actual writes. It turns out that if you're flushing to the media, then you're actually competing. The writes are competing with the reads, and that's why you want to actually bring in as little data as possible from the media itself. Is that clear in terms of the optimization? It's a pretty straightforward optimization.
Yeah, I think this is important to emphasize that, so here's the first example of where this is not flash washing, right? And we're handling the media differently, because think about an alternative array. It has the write allocation size or read allocation size of 1 meg. If it reads from flash, it's going to bring a meg in, right? And that's crazy in terms of latency. It's also crazy in terms of bandwidth, right? If you're doing that many IOPS, right? So I think this is an important point.
So you believe you can actually get by with less cache?
So the answer is you could get by less cache on the read-intensive application workloads. That is a true statement. Even for the write, because you could actually flush those things. But the one thing that, and we'll talk about some of the optimization we did on the write, but the write cache gives you something, and that allows you cache consolidation, so you reduce the wear level. We'll talk about that in a minute. So more cache actually helps in terms of life, managing life expectancy of the drive, of the flash itself. All right. So, adaptive write. This is the other piece that we actually used to do, and again, for the drives versus the disk, it didn't really matter, right? So imagine the case that you had brought in 16K worth of data because the host had written 16K. The host had read 16K. What we do is we actually keep the cache in 16 kilobyte cache page valid pages. So if it happens to have read, and this is not atypical of the hosts and applications, well, they read a whole bunch of data, but they modify a tiny bit in the middle, right? So they read 3 pages, but they happen to modify only 4 kilobytes in the middle, right? In the previous instantiation of the software, when it came to sending the data out, we will send the whole 4K out. There really was no advantage to just sending the 4K in to the drive. We will just rewrite the whole 16K out. So this is the case where now we actually recognize, we actually have what we call a dirty mask. That there's a valid mask and a dirty mask that determines how much of the actual cache line is valid and how much of it is dirty. In that case, we're only writing the portion that is dirty. We don't write more than that. Okay. Now, this actually helps obviously with the life of the flash, right? And if you think about the flash, typical page size on the flash is about 4K. That's typical of the flash devices. If you were actually writing 16K, you were actually now writing 4 of those cache lines inside the flash media itself. Now you're just writing what's actually important, right? Again, helps with the life expectancy of the flash media itself. It also helps with the backend throughput that you're actually pushing to the flash itself, right? Now, there's for the RAID 5, this doesn't really matter much because you have to do read, modify, write, because you have to write to the parity. But for RAID 1, it matters a lot because you're actually, significantly reducing the amount of I/O you're doing to the back end. So this is what we call the, sending the cache essentially to the flash media. So one of the things that we have done in the past, this comes from the drive days, and we've enhanced it for the flash itself. The data that sits in the cache, at some point in time we have to send it to the drive. But what we do is we actually have a backup algorithm that says how much dirty data do I have and how often do I need to run the flusher, right? If it turns out that the data you have in the cache is not particularly, heavily written, okay, then the flusher runs at a very low frequency. Let's say every 200 milliseconds, right? It wakes up every 200 milliseconds, looks around, and sees what's actually dirty and flushes it out, right? If it turns out that you're actually short on cache because the host is writing a hell of a lot of data, right, and you can't keep up, at that point in time, you actually kick up the flusher frequency and actually starts to span the cache pages at a much faster rate to flush them out. Now, why do we actually have this low cache, sort of lower frequency? Imagine the case that the customer is doing, a rate 5, and it's typical where people do rate 5 or rate 6, right? And if they're writing and you're able to actually hold off and not flush out because the write rate is not too much, if you wait long enough, you can actually build up what we call a full set size of the rate 5. So imagine it's a 4+1 kind of parity, right? The customer writes data 1, sometime later they write data 3, sometime later they write data 2. If you waited long enough and didn't send anything out, when it's time to actually send the data out, you can just XOR those data and write the data on the parity, right? Versus the case that if you were a little over-eager and tried to write it too quickly, you have to write the data 1, you have to read the old parity, you have to read the old data, you have to write the new data, you have to write the new parity, right? So a single I/O from the host will translate to 4 I/Os to the backend. Very expensive behavior, right? Versus if you actually waited longer, right, and allowed the cache to build up with the various bits and pieces, then all of a sudden 3 writes become essentially just 4 writes. A single XOR operation and 4 writes in the backend, right?
I'm curious, would that be reflected as a cache hit on the storage array itself if you're pulling the stats off the array, as an example?
Right. No, it will not.
Okay.
So this is purely on the back end,
okay,
right?
so just from my own personal experience on the 3-part platform, is there a way to determine what percentage of the workload is achieving
that behavior? Yeah, so you have to actually
Yeah.
look at the histogram of the I/O to the logical disks.
Logical disks.
So if you look at the hist LD, right, we have the logical disk. Those are the sort of the units that does the rate 1 and rate 5. So you specifically look at rate 5 and rate 6. Then you look at the histogram of the I/O distribution, right, and then what you will see is that the bigger the I/Os, right, they represent full struct writes. The smaller I/Os represent read modify writes. Okay, so if the write size is larger than the stripe size, it's a full stripe write. If the I/O size is smaller than the stripe size, then there will be read modify write. Even that we actually are a little more clever about. So imagine the case that you have, a 6,1 rate 5. Okay, and then now 5 of the data has come in, but the 6th piece just never came in, and the flusher says, I'm running cache, I gotta push this stuff out, right? Even in that case, we actually do a clever algorithm where we are missing just one of the pages, right? The 6th page that never came in. We pull that in, XOR the 6 together, write the parity and the 5 dirty pieces, right? So there's a mathematical formulation that says, if I have 2 out of 6, do I just do these 2 or do I read the other 3? So there's a math formula applied, right? So depending on the number of the dirty data you have, you apply this algorithm. It tells you, do I go read the old data from the other stripes, or do I actually read the old data from the current data, and then you just apply that, and it will give you the minimal number of I/O you have to do to the backend, right?
Okay.
So it's a little more sophisticated than what just this initial described.
Okay.
It actually looks at what's the best math for doing the least number of I/Os in the backend.
Okay. And along those same lines again with the cache, because our workload, for example, is almost entirely on the right side. Is there a way to tell how much of the cache is being used for reads, how much of the cache is being used for writes, and or controlling that at all?
So you can't control it. It's dynamic in nature. So it actually reacts to the load itself. But you could tell how much the cache is being read versus read. StatCMP will tell you what.
Okay.
Yeah, that will tell you how much the cache is used for.
Okay.
Okay. Any questions on sort of what the flusher does and why it behaves the way it does, right? I mean, so the service time, the flusher frequency could be as low as once every 200 milliseconds versus as fast as every 3 milliseconds. So it can react really rapidly depending on what's going on to the I/O that's coming in from the hosts. Okay. Oh, yeah, okay, you have.
Same thing, but it's
Okay.
different.
Okay. So, the other piece is sort of what we call the multi-tenant I/O processing, right? And this is the part that we have. So, if you have a drive, you want to have the largest stripe size as possible, right? Because it's so expensive to go to the drive. We talked about the expense of going to the drive, right? So, if you look at the way we do RAID 5, for instance, right? A stripe size on the drive is about 64K to 128K, right? So, the best way to think about it is if you have RAID 5 and you're reading 1 meg, how many drives are you visiting? Okay, right. If you're going every 64K, you can sort of take the 1 meg, divide by 64K. That's how many drives you're visiting to get your 1 meg worth of data. If it's 128K, you take the 1 meg, divide by 128K. That's how many drives you're visiting to get your data, right? Now, in the case of the drives spinning media, it's so expensive to go to the drive that if you're doing a sequential read, you actually want to do a bigger read, right? So you want a bigger step size, right? So when you're doing a sequential read, you don't want to visit too many drives because it's expensive to go to the drives and get the actual head spinning and so on, right? Now, in the case of the SSDs, they're actually pretty cheap to get to, right? And so you want to actually have much smaller step sizes, right? So let's talk about this example here. This host is doing a 128K read versus these guys who are doing all 4 kilobyte reads. Well, it turns out the data for these two hosts, some of it will be served by the exact same drive. Okay? That's just the nature of a wide striping system. So if I have 128K read comes in, and if the stripe size happened to be 128K in size, it would go to a single drive. While the 128K is in progress, there could be other IOs dispatched to the drive, but really, even though they're parallel to the drive themselves, when it gets to the flash media and is pulling in from the flash media, there's some amount of synchronization that is going on. So the 4K read, even though it's dispatched to the drive in a parallel, it actually will suffer behind the 128K. 128K has to get satisfied by the flash media before the 8K is processed by the device itself, right? So that actually ends up being worse for the latency of the 4K reads for this host too. So all of a sudden, two hosts can actually interfere with each other's behavior, okay? This does not apply to spinning media, but does apply to SSDs. So what we do, we actually have smaller stripe sizes for SSDs, 32K in size, which means that the 128K read from the host is broken up to 4 distinct reads on 4 distinct devices on the back end, okay? So all of a sudden, the 4K reads are competing with 32K reads as opposed to 128K reads, right? That gives you a much better behavior in terms of the I/O processing. And this, again, the game is all about I/O latency with these SSDs, right? People typically buy these things for the latency behavior. So last thing you want to do is to have a 4K read stuck behind a 128K read at the drive, right? And that's why it's broken up to 32K.
So Siamak, we should see a benefit of this in VDI, you think?
VDI is a very read workload intensive for us, right? It's also very write workload intensive, right? So essentially, and it's doing actually much smaller reads, so, and it's very latency sensitive. So actually, you should see a significant benefit from its behavior, right? Okay, so does that help understand what we do? We essentially, break up the system, wide stripe the system differently for SSDs, so that you always guarantee much smaller reads on the back end, because big writes or big I/O to the SSDs is not good. So that's really the motive behind this particular behavior. This is sort of so there is a second benefit from this behavior. So we just talked about the I/O latency improvement, but there's a second improvement that you actually pick up. Imagine now an SSD device failing. Now you have to reconstruct the device. Okay, so the reconstruction essentially means that you have to pick up and read from someplace else and rebuild the data. Okay, but the reads are always happening for us in the step sizes. So imagine that you have to we have these chunklets, but the chunklets are not the read load size, right? The chunklets is just this 1 gig things that is made up to make up the logical disk. But the step size is what determines how you actually reconstruct your logical disks, right? And if the step size is 32K, during the reconstruction, you're reading 32K at a time, right? By reading 32K at a time, essentially you're guaranteeing that not only can you rebuild it pretty quickly, but you're also not impacting the performance while the reconstruction is in progress, right? And we actually measure this. And sort of an interesting story, our SPC benchmark, right? One of the SPC benchmarks we were doing, during the benchmark, an actual SSD drive failed, right? And the actual numbers of the SBC benchmarks were not significantly different from when the SBC benchmark was running with all the drives healthy, right? I mean, this actually says something really cool about, the system behavior under failure, right? Where a drive fails, the system is actively reconstructing the data, and SBC benchmark essentially doesn't change in terms of the number of IOPS that is being delivered or latency that is being delivered, right? It's essentially seamless to the box, right? And a lot of it is around the fact that we're able to actually do 32 kilobyte step size reconstruction rather than 120 kilobyte. Again, for the spinning media, you really don't want to go there for 32 kilobyte over and over again. Once it's so expensive to get there, you want to pick up 120 kilobyte, right? So, of course, none of this can be done.
Excuse me, can you go back
Sure.
1 second?
Sure.
Thanks.
Any other questions on this? So, the piece that makes it all possible, of course, is the ASIC itself, right? I mean, the reason an ASIC gives us so much is there's a lot of work that ordinarily the CPUs would do. And if you look at a lot of current vendors that are coming with all flash, it's all done by the CPU, right? Which means that at some point in time, they're going to run out of not bandwidth, but CPU instruction, how many they can execute, because they're just giving so much of the work to the CPU itself, right? Now, it turns out that the other way to think about it, there is one more way to think about this, right? That yes, you can throw CPUs at it and get lots of great IOPS. But then when it comes to providing additional I/O services, priority optimization, automatic, AO, SR, all the various services, remote copy, they're added tax to the CPU. So the guys who are actually putting out great numbers, all CPU systems, all the flash vendors, right? They have very thin I/O services. If you think about the added services they provide, from disaster recovery, right, for instance, remote copy, to the ability to do tiering, to the ability to actually do fine-grained measurement, quality of optimization, all those additional services, which as they add, they're putting on the same CPU that is completely booked today to do I/O services. For us, the I/O services are primarily done by the ASIC, which means that the CPU is available to do all these additional services. So I worry about the case where if my CPU was completely taxed, right, and all of a sudden I had to actually add additional service. For instance, Federation adds another service to the box, right? Every time you add a service, you have to worry about what it's going to pay for it in terms of the CPU, right? So, we've sort of talked about what are the properties of the ASIC, and it gives you the ability to connect all 4 nodes, right, without a switch, which is a fantastic property. You don't have to have an external device to connect these things, right? One less failure model to worry about when everything is passively connected. We have mixed workloads because the ASIC essentially allows us to parallelize the streaming workload versus the random I/O workload. It's a combination of the ASIC and the software. The fact that the software itself has so many threads. On a given controller node, we have about 2,000 threads that work on I/Os, right? It's unlike the other systems where they have a single thread that is doing front-end I/O, one single thread that is doing the back-end I/O. What we do is on our system, we take a couple thousand threads, each one picks up an I/O and carries the I/O through its entire life, right, from the read to the write. It allows much better parallelization. Go ahead.
I was just curious from a failure handling standpoint. Traditionally, I think even applies to the current generation of 3-bar things. When you have a pair of nodes, they are peered in the same chassis. They're installed horizontally. I'm curious if you guys have thought about, or if it's even possible, to peer in a vertical manner instead, especially in the case of the 7400 series. So you could lose an entire chassis, and at least one node from that pair would still stay online. Because I think with the current generation of 3-bar boxes, if you lost the chassis that had that pair of nodes in, you would lose access to all the stuff that was behind that pair.
Yeah, so we actually had a design called quad port. In the quad port model, quad port.
Okay.
So this goes back long ago, right?
440.
Yeah,
The 440.
exactly. So in that model, each drive was connected to 4 controllers.
Okay.
So essentially, as opposed to each drive being connected to 2 controllers, we had the cages. If you look at our cages, they actually have 4 ports coming in, right?
Yeah.
So we actually had software and services ability to actually connect the cage to 4 controllers, right?
Okay.
And all of a sudden, because the access to the drive was preserved, right? You could actually use up to 3 controllers. It didn't really matter what combination. You could keep the I/O services going, right? It turns out that the physical connectivity became so expensive because you have to actually burn so many ports to connect to the back end that it becomes cost prohibitive to do that, right? And so the question is, in future, as SaaS SaaS is a very different animal than fiber channel in terms of the physical cost of the ports and the physical connectivity map, right? So it is possible for us to resurrect the ability to actually do quad access, and then all of a sudden you actually can solve the problem we're describing, right? So it's not really a technology problem; it's sort of a cost problem, right? And a physical topology problem.
But if you're not going horizontally and you're going across chassis, so node 1 and node 2, or node 0 and node 1 are crossing the chassis, so being in the same chassis, that solves that particular problem as well, right?
Well, you still have the problem of 0 and 1 fails. If it was 0 and 1, and then you had 1 and, for instance, 3 being, the node pair. If 1 and 3 fail,
no, yeah, but I mean, if they're
again,
across if you're across chassis, you can lose that chassis with that pair of nodes, and it's still.
I see. For the 7400, you're saying specifically,
yeah,
right? Yeah. That requires. You could do that. The problem is that then you have to deal with the upgrade story. If you have a 7400 that started with 2 nodes and they want to go to the 4 node, and then you have to actually completely relay out your data, relay out your physical connectivity. That's really the issue with that. What was just described.
Okay.
But today we can survive with that vertical cage layout. You can survive a cage failure, right? With HA cage configuration.
But, as long as
he's talking about the whole chassis.
No
chassis. No chassis. Yeah, that's awesome. Okay.
Okay.
So that kind of request the low latency cache mirrors you might want to.
Yeah. So one of the things that is kind of an interesting property they have, and I described this.
I'm gonna move that chair. See, maybe you need to move move the board.
So imagine a two controller system, and a host is performing a write to the box, right? And almost everybody has to do some sort of cache mirroring to the other side, right? So think about the way typical cache mirroring works. You have a piece of memory on the other side. So the data arrive from the host. There's an HBA these are the HBAs that are connecting the host, right? And then you have a piece of cache line that needs to be mirrored before you can acknowledge the IO host. Now, almost all systems connect some sort of industry standard InfiniBand, fiber channel to connect these guys together, right? Some sort of off-the-shelf technology, right? We actually connect these using our ASIC. Okay. So one of the nice things about the property of the ASIC we have is we are able to actually send data from one controller to the other controller. So this is the CPU sitting here, right? And the CPU is essentially what is commanding the ASIC to do something. So the CPU can command the ASIC to transfer the data from this cache line to this cache line, okay, without actually notifying this CPU at all. So this CPU is not involved in the transaction at all. So you send the data, you mirror the cache to the other side, you write what's called the transaction log again over the ASIC to the other side, right? So this is the data from the customer, this is the transaction log that describes the data, and then you acknowledge the host. And then sometime later, the cache line is hit, you hit the disk, and you don't need the cache line, and you kind of erase the transaction, saying the transaction is complete. During this entire process, this CPU was never involved. Okay, no interrupts, nothing. You didn't understand what you were doing. It's unlike any other design. If you think about an InfiniBand design or a fiber channel design, or any of that stuff, right? There's no notion of dumping data to the other side without notification, right? We have this ability to dump data without notification, right? Which means that you have much better latency and much better throughput because the CPUs on this side were not involved in any of the transaction processing. Okay, that's unlike any other design, right? Now, so this is the case that the host happened to be attached to the controller that was managing the IO. Imagine the IO needs to be managed here, right? The same model applies. You dump the data to the other side, again not telling him that you did this, but because at the end the processing has to be done by this CPU because he owns the cache line, you send a notification that says, I have sent the data to you, there's a copy of the data sit here, there's a copy of data that sits here, please process it. The CPU gets involved, writes the transaction log, acknowledges it, and goes out. Again, the same processing, the initial processing of dumping the data completely gets done by this CPU. There's a second CPU handshake, and off you go. 2 CPU handshakes. Versus an InfiniBand or fiber channel, I can sit down and do the number of CPU handshakes is up to 4 and 5 CPU handshakes, right? And so it's a and because we can actually now scale up to 8 nodes, right? In the case of 7450, up to 4 nodes, because of the way the ASICs are designed, and each ASIC essentially has 3 ports coming out of it, each port is physically connected. When the CPU commands the ASIC to do something, again, there is no hop, there is no going through somebody else. There's a direct pack from every single controller to every single controller. Right? Again, all of it. When we were designing the ASIC, we very carefully sat down and said, what are the things that we need to do for the ASIC to do so that the CPU doesn't do it? And that a big part of what we do is just duplicating the data from the host, right? Every single host I/O coming in from the host has to get duplicated. Those are the writes. So that's a large part of what we do. And the CPU can just sort of offload that to the ASIC in terms of duplication. Right? Very nice design.
I'm curious, because the 3-part architecture is 10 years old or so at this point, how come you think there aren't any other of your competitors that have taken that and tried to steal it and create their own ASIC, for example? And
it turns out that they all create ASICs. In fact, when we talk about other vendors, every one of them has a sort of a specialized ASIC inside, but they choose to use the ASIC slightly differently, right? They tend to choose ASIC for some amount of offload within, for instance, XOR processing, or some amount of depending on the vendor, they all use slightly different. It may not be an ASIC, maybe an FPGA, right? But it turns out that having an ASIC that does all of those, the XOR, the link engine, it's actually a pretty daunting undertaking. It's quite expensive to develop an ASIC that is that big. It has a memory controller, right? Often their ASIC doesn't have a memory controller, right?
Yeah.
So it's not cheap to actually develop an ASIC like this. A lot of customers choose, a lot of other vendors choose to sort of have a small special purpose ASIC that does a specific offloading as opposed to this massive undertaking. For us, the development ASIC takes about a year from end to end, from the time you actually do the design until the tape out, more than a year and a half for it to come back. It's 2 years by the time the chip is on the board, another year for the system to go out. So it's really a 3-year undertaking from the inception of an ASIC thought, right, to the actual product shipping is over 3 years, right? So
HDS does a lot of ASICs. If you look
Pardon?
at HDS does a lot of ASICs in their systems.
Right.
The VSP and the VM, HUS VM, 10, 12 ASICs in it.
But
But I think
it's
the
the
ASIC, the key is the ASIC is just a component, right?
Yeah, yeah.
There's also the
Software, yeah.
software layer, right? The virtualization engine, the multiple controllers. I think that sort of end-to-end view, and taking a software-centric approach, right? An OS-centric approach, I think, is where the other folks, correct me if I'm wrong, have fallen down.
Yeah, the Hitachi, for instance, the perfect example is the Hitachi. I mean, it's a great box, but again, every single LUN is controlled by a given controller, right? And you have to be very careful, right? They actually tell you, they go through lots of trouble to say, if you do too many LUNs on a given controller, you will overrun the controller or cache line or whatever, right? And you have to make these tiny little LUNs, right? And then you actually have to have, the tip in, and the biggest problem we have is with customers that come from a Hitachi world, right? Because they have all these tiny little LUNs. They have these expectations that they're going to make these 50 gig LUNs. And we're like, why are you making 50 gig LUNs, right? Just make 500 gig LUNs, right? Well, but you can overrun whatever. It's like, no, you can't. Make a 500 gig LUN, right?
Yeah.
It's just really hard to get them over this sort of mindset of, oh no, I have to make tiny LUNs, otherwise the performance will not be good.
Yeah.
It's just, you're solving a problem that you don't need to solve. But you have more experience in this area.
Yeah, I was going to say, Ray brought up the point of the ASICs. You're absolutely right. There's probably 10x the amount of ASICs within a single FPSP than what we have in 3-part. The key piece of that is what the ASICs are used for. They're very
That's
specialized.
what I was trying to say. Yeah,
Right.
yeah.
And so if you have them on your chip pairs, they're very focused upon the access of data that's coming from a host and how to manage that to a given rate and parity on the back end and dealing with the traffic associated. Then on the vice versa, if it's on the CHPs,
Right.
on the back end on your ACPs, now you're trying to manage just the opposite. Okay, we have all of these disk drives out here. How do we manage the traffic and what's the access to the cache? But all of those operations are very specific to what those ASICs are doing from back end to cache and front end to cache. The big difference there is once you start looking at the CPUs, as you add on those additional products, i.e. your business copies, your replication, everything else, the first thing we warn you about is you need to maximize your cache right now in order to make sure we don't overrun the capabilities of performance as you add on those other feature sets. Because every time you add another copy to it, every time you turn on business copy, every time you turn on your remote access, your continuous access, or I forget what those names, that begins to negate the capability of processing power to happen from the CPUs. It's just the opposite here. What your CPUs are doing are actually being offloaded directly by your ASICs all the time. And so you're not getting any CPU offload necessarily typically from those ASICs. In the whole of the story, you are, obviously, because you can try and run all that through your CPUs and be dead. But the incremental amount that happens there, the amount of function that happens there, is very specific. So these ASICs understand the entire story of what's happening in the array. That's how they can move data from controller to controller without notification. You would never get that done on a DSP or any other array for that matter.
So, I mean, the best way to think about it, you know, all the other array vendors build cluster volume managers. Right? In other words, their LUN management, volume management is clustered, so they can fail over. We actually built a distributed volume manager. Okay, it's a very different design. Okay, in a distributed volume manager, a given volume is actually broken up in tiny little pieces and is managed by all the controllers in the system. And we really did design the ASIC around a distributed volume manager as opposed to clustered volume manager. You will design the ASICs very differently if you were building a distributed system versus just a clustered system, right? And a lot of the people that actually come from distributed HA background, right? So that's really the design model that is very different, right? And so I just described this case where the I/O comes to this host, and this I/O that is coming to the host on a 4-node system, there's only a 25% chance that it's actually managed by that host, because we fine-grained them. There's a 75% chance that the I/O is managed by some other controller, right? And so it's a little unintuitive because there's a little bit of cost to go across, right? But the nice thing about this model of always having the I/O go 75% I/O go someplace else is that if you have a given LUN, and that happens to be the most important LUN, and all your I/O is happening currently at that LUN because they just started some sort of database load application, some sort of streaming application, some sort of backup application, it's guaranteed that that workload will automatically get dispatched to all the other controllers, right? All the other drives that are attached to those controllers, all the cache lines that are attached to those controllers, right? So that's fundamentally different, right? Versus everybody else where they build a LUN, right? And that LUN is managed by that controller. And all those ASICs that was just described, they are designed to take that I/O on that controller, manage it in that controller, and on that controller send it to the back end.
Now,
Okay.
in an 8-controller configuration, the ASICs have eight lines or 7 lines?
So on the previous generations, they had 8 lines. In the current generations, we put 2 ASICs.
Also,
Each ASIC has 3 lanes. So so it's still a full mesh configuration, right? But the nice thing about putting 2 ASICs on a bigger system is that means more memory controllers, more memory channels, so you get more bandwidth, and you get the additional lane. So you kill 2 birds with 1 stone, so to speak, right?
And also, I recall being told at some point on the dual ASIC design where like an I/O request would come in and the pair of ASICs act as like a pull thing. The ASIC says, "I'll handle that I/O," and the other one says, "I'll handle that I/O."
That's right.
And if in the rare event an ASIC dies or fails, the other ASIC stays online and continues to process I/O.
Yeah. So what you described is what we call cache coloring, right? It turns out that the design is somewhat non-uniform memory access when you have 2 ASICs, right? So managing the memory becomes very important in terms of balancing the memory bandwidth on both, right? So you don't have, the same way I said, I don't really want all the I/O to be processed by this guy, I want a distributed amount. We do the exact same, we do cache coloring, so all the I/O that comes to the cache isn't handled exactly by one ASIC. I want both ASICs to equally actually share the load. So we actually do what we call memory coloring. This is sort of NUMA behavior, right? We color the cache lines and then go back and forth. And sometimes we actually prefer a specific cache line because we know that it's attached to an ASIC that is connected to here. So I dump it to this ASIC because it's cheaper to go from this ASIC to here than from the other ASIC, because one ASIC is directly connected to controller A, but the other ASIC is not. So you want to send the data from the locally connected ASIC. So we actually do this careful balancing, right?
Okay.
It's a little more esoteric than it's probably worth talking about.
Don't you sometimes feel that you're doing a lot of workloads on the ASICs as opposed to the CPUs?
So that's a really good question. Are we kind of running out of ASIC juice, right? The answer is, the Harrier, which is the current generation ASIC that we're actually using, right? Right now, on the 7450, we're running out of CPU still. We're doing 500,000 IOPS, 150,000 IOPS at 7 microseconds. And the thing that we're running out of is not ASIC. We're running out of CPU. Right? So that just tells you something that we over-design the hell out of these things. Again, because we anticipate these things being in the field for 7 years, from the date of the inception to the date that these machines start to come offline and they retire, right? So if you really are designing for something for 7 years, think about, imagine, can anybody imagine using Intel CPU for 7 years? No, right? I mean, they have to go much faster. So we have to over-design the hell of these things for 7-year lifespan, right? So by the time they come out and they actually are being used, the CPU essentially becomes a bottleneck for us, and it stays the bottleneck for at least 2 generations, right?
So
Okay,
let me
so why don't
suggest we
yeah.
take we're gonna take a short break. This is gonna be a short break, and again, I've told you guys we usually do these tech days in a day and a half, and since we're doing a lot, I'm gonna work you hard. So let's take a 10-minute break so that we can start right around 10:30. If anybody needs more coffee, you can either go to the coffee shop over by where breakfast was this morning, or behind Trader Joe's. Behind Trader Sam's, there's that where we're gonna have lunch. They also have coffee there, or there's some make cups in the back that Rob brought his coffee maker with him. So let's take 10 minutes.
So let me just ask you real quick: is this the right level of technical detail? Do you guys want deeper or shallower or whatever? But is it good? Is it reasonable in terms of the?
Yeah, let's go around. I mean, I know some people want more, but others here, right level.
If you want more, raise your hand. If it's good, raise your hand.
Okay, all right. So I think it's the right level. We'll take Nate out to the back here. And meet him
Yeah, you guys can have Nate on your own. Okay, well, welcome back. We're going to continue with a deep dive on HP 3PAR.
I think we've sort of probably beaten this horse to death now. Talk about some of the. So this is one of our kind of famous slides that describes really the architectural delta between the box as designed initially and the rest of the industry when we started. So this is the typical of what the world looked like when we started. A really sophisticated architecture was what we call the monolithic architecture. Think about DMX, right? Where they were built from shared memory infrastructure, lots of specialized hardware, fantastic system, but extremely expensive to start with because you had to buy these front-end directors and back-end directors and all the controllers in the middle, right? And it really was a really expensive system. And it also, go ahead.
Sorry, and complicated.
And complicated, exactly. And involved really a lot of management at the application level. So what we fundamentally started with was a different model. We started with almost industry standard servers and added an ASIC that creates full mesh. In other words, we described the case that each ASIC has a dedicated lane that connects to every other ASIC, so you don't actually require a switch. Add to that ASIC not only the link functionality, but the functionality required to offload the CPU to the storage workloads, such as XOR computation, zero detect, and so on. So that's the fundamental building blocks. A full mesh ASIC that connects everything with the ability to do storage-specific tasks. So the nice thing about this, the cost of an ASIC is not that much. So you can start with 2 nodes that are essentially industry standard servers with a function-specific ASIC added, and then you can actually go up all the way to the 8 nodes without the fundamental, capital outlay required to go to this point-to-point switch connection. There's this huge network that you have to build ahead of time. Okay, so that's the fundamental model. Now, what makes it all tick is really the software. The software of the distributed volume which we just talked about, DHA, all of that actually makes the system what it is today, right? And so to go back to why don't other people build ASICs? You can build an ASIC, but to build a system is a very different story based on the ASIC model itself, right?
And there's also the distinction with clustering versus how your architecture. Every node is standalone. There's not a shared OS.
Exactly. The image. So what Nate is pointing out, every single one of these controllers is running its own distinct OS. So its address and memory boundaries are all protected, so that if this unit fails, it's independent of any other unit that is connected to the mesh itself, right? So some of the nice thing about this particular design is the load balancing and the symmetric nature of the box. So one of the nice things, so let's go back to this for a second. If you look at it, this one does front-end stuff, this one does back-end stuff, and that's all it will ever do, right? So you better make sure that the sizing is correct. Versus this model, the same controller is doing front-end and back-end. So in other words, the unit of add, which is a controller, is adding both front-end and back-end and CPU and cache at the same time. Okay, and then because the behavior inside the box is dynamic, in other words, there is no specialized CPU for the backend, specialized CPU for the backend. The CPU is the CPU. If the workload becomes cache read intensive, the CPU is just going to switch and provide all the I/O to the host, right? There is no work to be done. If it turns out the I/O is, random I/O to the backend, to RAID 6, where there's a lots of stuff to do on the back end because you have to do all these RAID computation, but there's lots of interrupts on the back end to deal with. The CPUs automatically start to handle that load. You don't have a special task or a special CPU set aside for front end and back end, right? Everything's symmetric within the controller, right? So we adapt to the load itself. It's a front end load, the CPUs are doing front end work. If it's a back end heavy load workload, because you're doing data migration, you're doing RAID rebuild, the CPU will automatically adapt to that particular workload. So that's a very different sort of design model where we don't set aside specific functions, right? It's more than just an ASIC specific function, it's software specific function. It's distributed across the entire system, right? So, we'll get the low latency fabric from connecting all these ASICs. You get the workload that is actually distributed across all the systems. So you have essentially a much nicer distributed design system. So add to that this notion of white striping. And so the white striping, when most people think about white striping, they think about it in the context of disks.
Maybe before you get into the white
Sure.
striping, if you go back here, so maybe the point to talk about here as well is the 8-way controller, right? And eight node scalability for flash.
Sure. Yeah. So if in the world of an ASIC, if in the world of SSDs, the bottleneck is the CPUs, you ever bring to bear as many CPUs as you can, right? That's really what it comes down to, right? So if the unit of a controller has only 2 CPUs in it, you keep adding controllers until you get a lot more CPUs. All of a sudden, you have 16 sockets available to do all your SSD workload. That's kind of unique, right? And not only that, you can actually have all those 16 sockets on behalf of any given LUN because of the distributed nature of the box. Is that the point you were trying to get across? Yeah. So let's talk about white strapping a second. So we talked about, when initially we talked about white strapping, everybody focused on the drives. For a good reason, because the drives were the bottleneck, right? So if you could actually bring to bear all the drives to a specific LUN, that really raised the performance profile of that specific LUN. Okay, so that's an example of a given LUN distributing all of its data across all these little disks, right? And so what happens is that if you're doing random I/O to this particular LUN, you're using all the drives in the system to actually get the maximum performance from the box. Okay.
No matter how many drives are in the system, it always drives.
It white straps across all the controllers and all the drives. Yes.
It does vary depending on the size of the LUN, though.
Right.
So if you have 800 drives, you have to have a LUN that is large enough to span.
Oh.
And also the drive type, right? So if you have a FC LUN, obviously it will be on the FC drives. So if you're mixing FC and SSDs, and you specifically say I want an SSD LUN, you only strap on the SSDs.
And you can still split it out into CPGs of subsets of.
Right. If you choose to, you can always do that. But the default behavior of the box is to go on all the drive, on the maximum number of drives that would actually fit the LUN itself, right? So now this is great for the case where you actually have to do random I/O. All the drives are being, and in fact, the way we do this to demo this, we'll make a 2 terabyte LUN, start doing random I/O, and then you will see all the drives are doing I/O at the same time, right? That's a great demo to show because it's not really a demo; it's just the behavior of the box, right? Try this on any other array. Make a single 2 terabyte LUN, start doing random I/O. You will only see a subset of drives essentially heating up. In this case, all the drives start to heat up and actually work on your behalf. It turns out in the SSD world, this now means that because the drives are not, we don't have a full mesh connectivity on the back end, right? A given drive is connected to only 2 controllers. And even then, a given drive is managed actively by one controller at a given time. It has a failover capability, right? So if this drive is managed by this guy is managed by this guy, right? But because we're actually, and a given piece of the LUN that is managed by controller is managed by controller that is attached to the physical disk and owns the disk at that point. It really means that we have to actually white strap the entire LUN across the controllers. And I talked about that a little about that in the case that we were coming to a given controller and we were making a determination if that controller was the owner of that workload or not, or that work item or not. So in practice, what it means is a given controller owns the data. It means that the cache line that is active for it, the backend I/O processing, the transaction log processing is actually controlled by that controller. Okay, which means that a given LUN automatically is actually strapped across all the controllers and all the system resources, CPU, cache lines, backend, actually comes to bear and actually help that particular controller. That becomes a very important thing in the SSD world where the bottleneck is no longer the backend, it's the CPU, it's the cache line. It's how fast you can actually schedule that thread to go fetch the data from the backend, populate the cache line, and answer the host, right? It turns out that you're quickly run out of CPUs to do that. Now, having the ability to actually strap the SSDs and using the cache lines of all the controllers means that everything works much better, right? And so the 500,000 IOPS that you're talking about, we're getting out of the 4-node 7450, these are on fully distributed LUNs, right? No tricks, no funny, LUNs where we use a Lua and have an optimized path. None of those techniques. Essentially, you're doing round robin, fully distributed runs in the system, right?
Siamak,
Yes.
I want to throw something in here because there's an obvious benefit there, but from a customer point of view, something that we come across a lot is in putting together any array, the typical first steps are maximized for performance, capacity, and availability. And when you're building out that array, you know, someone from company X comes in, they sit down with you, and they figure out how they're going to map out the array and lay out the array. Then after you have it laid out, I should say during that layout process, there's some basic assumptions around the application that's made, or whether it's historical, whatever the case. You go through that layout process, and eventually the box lands on your floor as the customer. And when that box lands, you implement it based upon the RAID expectations that you had set in that whole layout process. Now, my common question to customers now is what do you do, or what does your company do when they begin running testing to validate the performance, because you know the capacity is right, they start validating the performance of that application against the storage, and they find that they didn't need as many disks committed in order to reach the performance threshold. Do you re-architect those disks and reduce the number of disks you have there? The obvious answer is what? No, it's performing well enough, so I'm not going to touch it. Now let's take that the opposite direction. You laid it out and you realize that you don't have the performance you need. Now what do? You buy more drives. 9 times out of 10, you buy more drives. And in reality, you probably had enough drives in your entire array. You could have simply shrank the one that was overperforming and then put it in someplace else to try and meet that need. But you're definitely not going to do that because why? It's far too complex to go through all of that problem, to try and figure it out, make shifts to CPU and cache and everything else. You will not do that. It's just the opposite here. When you lay out the array, it's already laid out from the disk drive point of view. All of your chunklets are where they're going to be. All of those subsets, those yellows, they're already assigned. They're not committed to RAID 1, RAID 5, RAID 6, or this 8 drives, or these 16 drives, or these 9 drives, or whatever the case. So your ability to make those shifts on the fly based upon RAID is the difference between, in most customers' cases, when they've gotten that initial box, a week to try and get your performance right, and a few minutes to make the shifts right here in the 3-bar array. So that's how it translates to the customer. I just want to make sure that we sort of...
I have a quick story from a customer standpoint. Back in 2000,
Very illuminating, thanks.
Back in 2008, I bought a T400, a dual node T400 with 200 drives. And at that point, the dual controllers were maxed out. We bought a NAS system, and we put a file system on it. I asked the NAS company, is your file system thin provisioning friendly? They said, yeah, absolutely, no problem. And so, because we didn't have much time for testing, when I created the file system, I created a file system to X amount of size, and then all testing passed great. We were running in RAID 5, 3+1 at the time. And then as I saw the stats grow, the written space on the back end was growing and growing and growing. It wasn't shrinking. And that was primarily because the workload we had, we were having to write and delete terabytes and terabytes every day. And so I noticed about a month and a half into it, I'm like, if this keeps growing, this will exhaust the capacity of the drives. And I can't add one more drive without adding 2 more controllers. And that's a very expensive thing to do. And so I did some calculations with the help of my SE at 3-bar at the time. And I decided to start a dynamic optimization process to convert the array from 3+1 to 5+1, still staying RAID 5, but that reduced the amount of space required on the back end. And I ran that process 24 hours a day, 7 days a week for about 3.5 months on a very active application. And I was the only, outside of me communicating to other people on my team, I was the only person in the company that knew that this conversion was going on. So it was rewriting approximately 80 terabytes of stuff in the back end while all the applications were slamming it 24 hours a day, and there wasn't anyone. And I knew at that point I was blown away because I had made a big mistake on my end, but I had also known from the start that I don't need to plan as much up front with the 3-bar stuff because I have those options available to me.
Thanks, Nate.
That's a good story, yeah.
Yeah, so I mean, that's one of the nice, the other sort of there's a lot that goes into sort of allowing you to do that, because there's lots of bandwidth and IOPS in the back end that is being used, right? And that's competing directly with the host application. So we spend a lot of time optimizing that particular back-end workload that is doing stuff like the layout or dealing with failure, so it does not impact the actual host application. In fact, the way you can see it is that if the system is idle, the tuning process runs at line rate on the back end. You kick up the host I/O, and all of a sudden that tuning application performance drops significantly, just because we really need to sort of give them the maximum. There's a lot of work that goes into sort of taking into account and making sure that you don't actually impact the application workload, right? And sort of along those lines, one of the things that we've added, is the case that you add new disks or you add new controllers. We have a command called tunesys. So essentially, you just run the command, and it will go and analyze what's changed. New drives added, new cages added, new controllers added, and it makes the best decision about the layout, and it will just apply those layouts. Because the fact is that the world changes, right? The initial layout decision you make is appropriate for physical environments that you're in. But as your physical environment changes, and as you add more disks, you add more controllers, it's in the past we sort of depended on the customer to type the tune command, right, to sort of relay out. But now
I'm curious,
sort of,
if you were to add extra cages, does in for example RAID 5 config, if you have 3+1, you add in two more cages, does that tunesys command keep it at 3+1, or will it expand
it does. It does that. The reason we actually keep it 3,1 and not go to, for instance, 5,1, even though the cage allows you to do that, is because we kind of give the customer the benefit of the doubt that they've decided that their workload is such that, for instance, they're doing sequential writes that are exactly 600K, and then they can actually get full strike writes. Because if I now go 5,1, all of a sudden I need to get 1 meg writes for them to get full strike writes. So because we don't want to sort of, that could actually change the performance characteristic of the box, and that's why specifically we don't change the RAID characteristics, but we change the layout characteristic, right? And in fact, what we do is that we make lots of decisions about what's the best way to make the layout characteristics. If it turns out that if you're just adding disks, we just move the chunklets from one disk to the other disk. We don't do the relayout. If you added controllers, we do a full relayout of the volume, right? And if you added cages, we do just a logical disk relayout as opposed to a full volume relayout, because new controllers haven't been added. So it's a very clever algorithm in terms of figuring out, is it an internode or intranode optimization that needs to take place? Is it an interdisk or intra-disk optimization that needs to take place? Takes all those into account and just starts the command and runs, and you can sort of monitor it, but it may take 24 hours, 48 hours, whatever it will take to actually complete the task.
So Siamak just mentioned the layout process and what goes on there. Now if you think about that from a customer's point of view, in that same situation, whereas he was referring to going from 3+1 to 5+1, or doing a full layout change based upon adding another drive shelf or controller, etc. In your typical customer scenario, in your traditional array, whatever array that's out there today, the ability to lay out is completely different from what we have here. Specifically in that if you're adding another controller, your layout is specific to the RAID that you've chosen already. So you're relaying out or laying out or adding on another RAID group, another metabol, another hyperbol, etc. That's where your contingency is. So you have to make a change on each one of those within your system in order to get maximum utilization. The key piece here is the physical underlying layout is already there, i.e. the chunklets. Those components are already there. Now you're actually giving a profile or a, what's a good word, Siamak?
We call it reservation-less pools. I mean, that's the best way to think about it. If you think about the traditional model, when you create the physical pool, it's an actual physical pool. You take all the disks and put it in the pool as your RAID 5 pool, your RAID 6 pool, right? And the disk is physically committed to it. Our pools become CPGs or common provisioning groups, right? They really are more of a template than an actual traditional pool, right? We call them reservation-less pools in the sense that there's no physical space committed to it. Maybe a tiny bit so that you can get your initial layout going, but it isn't, a terabyte. You define the maximum size it can grow to, but that's just the maximum size that it can grow to, right? You don't have to define that. So as you commit space and you draw space from it, let's say TPVB is created and it wants to draw a space, it goes to the CPG and asks for space. Then the CPG goes and asks the system for space. So these chunklets that are pre-initialized, ready to go, they don't have an identity, a pool or a RAID 1 or RAID 5 association. Okay? when the CPG runs out of space, it says, I need space. And then at that point in time, we go in and pull these 1 gigabyte chunklets and form the RAID 1 or RAID 6 grouping and commit that to the pool. And the pool immediately hands it to the consumer at that point, a volume or a snapshot space, right? And then the inverse is also true. If a volume sees a lot of zeros coming in, okay, that space gets consolidated and then returned back to the CPG, and the CPG can be compacted so the data then flows back to the system. So the space goes both ways, right?
And so to be careful, when he says pools, he's meaning every disk drive of a single type. So he's not referring to tons of imagining your typical array today, your typical traditional array, they're setting up thin provisioning. They'll say, we want to set up this RAID type, and then we'll have these, these 8 metaballs or these 9 whatever set up into a single pool to do thin provisioning, and everything else we're not going to do thin provisioning. He's not talking about that. Every disk of a RAID type, every drive type is all within a single pool. So all of those are behaving the exact same.
Right. And a point of clarification, you can mix drives sizes.
You can.
Drive types.
You can.
You have a pool of 1 terabyte, 2 terabyte.
You can have the entire array be.
Yeah, you could make choices. I mean, so we have customers that have made, they for administrative reasons, for instance, the same array is owned by 2 departments, and then departments buy the disks separately and say, hey, I don't want you to use my disks. So they make a pool that specifies the exact physical disks that can go into that pool, right? I mean, that's a choice of the customer because, for budgetary reasons, they decided that these are my disks, thou shalt not use it for something else, right? So that's a choice. We leave those choices to the customer. The default behavior is to use all the disks, right?
And so
But you can choose not to.
From a management perspective, the key difference there is you don't set up chunklets based upon thin provisioning, and then another group based upon not using thin provisioning. You don't set up, we're going to do this part of the array thin and that part of the array not thin. All of the arrays are ready for thin all the time. In your typical array that you're probably, our competition out there, if you're really going to use thin provisioning and if you want a high level of performance, think about it really bad. If you're going to do that, then, set up this amount to be ready for thin provisioning and provision it in a certain way, and now the other one that's going to be fully provisioned, do RAID 1 and do whatever you want and so on and so forth. You don't have that issue here. You are ready to go all the time, and it's far faster to implement for the customer. Sorry.
Right. Perfect.
I think one of the more interesting points, just to close on this slide, Siamak, this is one of the cases where flash and spinning work well in the same architecture, right?
Exactly.
This is
Yeah.
nice case.
For the spinning media, it worked for a different reason.
Yes.
Because you really were depending on these mechanical devices to get their act together to get you the data, so you wanted white strapping.
Yeah.
Right. For the case of the SSDs, it's not these guys that are your trouble. The trouble spot is here. That's why you actually want to actually use more of the controllers, more of the back-end bandwidth to actually be able to get to the workload itself, right? So they work equally well, but for slightly different reasons, right? So it turns out that when you have lots and lots of performance, you need, and then the bottleneck becomes the controllers managing workloads and concurrent workloads on the same array becomes a big problem, right? In the past, if it was drives, you could essentially drive the different workloads based on the drive type. So important workloads went to FCs, unimportant workloads went to the nearline drives. The cache didn't matter because we couldn't manage the cache in an autonomic fashion. The CPU didn't matter because you had lots of CPU. So the two workloads can stay out of each other's way. In SSD arrays, that's no longer the case, right? Because you're actually sharing the same work pool, and you could actually run out of. And in fact, what you could do, you could even say, this guy only uses 10 terabyte versus the other guy uses 90 terabyte. But the 10 terabyte of SSD can make you run out of cache, can make you run out of CPU. Okay, so all of a sudden, your unimportant workload could in fact impact significantly your important workload, right? And so the old technique of giving less capacity just doesn't work anymore, right? Because the smaller capacity is so fast that it could actually outrun the array itself. Okay, that's where the priority optimization becomes a very important feature, right? And then think about priority. The two performance characteristics that everybody looks at is IOPS and bandwidth. How many IOPS am I delivering? What bandwidth am I delivering, right? And those are the two primary issues that you have to contend with. And actually, they run out on an array, right? The bandwidth runs out because you're using too much of the bandwidth on the ports, or you're using too much memory cache bandwidth, or you're using too much back-end bandwidth, IOPS runs out because you're essentially outrunning, on the modern SSD machines, you're outrunning the CPUs. The CPUs just can't keep up with 500,000 IOPS. So you have to sort of manage those things carefully. So what we've created is this notion of priority optimization, where you can take an application and apply these two knobs, independent of each other or at the same time. You could say this application gets no more than 100,000 IOPS. Okay, and at 100,000 IOPS, we start to throttle application, and that could be the only measure you put, or you could also say 100,000 IOPS or a gigabyte per second. If either one of those metrics starts to actually exceed, you actually start to throttle the application. Okay, you could actually have a second application with a different set of IOPS or a different set of bandwidth, and you can have as many applications in the system as you want in terms of defining the quality of service, as many volume sets or autonomic groups that we have, and you can sort of make them subject to these IOP or bandwidth limitations. The other nice thing about this particular application is that you could set these things and they take effect immediately. There is no build-up time, there is no computation time. You put that in place, milliseconds later, the application starts to get throttled down. And because the impact is instantaneous, you can actually change the behavior. Imagine you have a backup application that is really bandwidth heavy, right? And you really want them to use the bandwidth, but only from midnight on. So you can actually configure a scheduled task that says, this particular application, which is in my backup application, can use 6 gigabyte of bandwidth, because by God, I want it to run and finish. But at 6 a.m. when the production starts, I really don't want, let's say the backup window has run out and the backup is still continuing. For whatever reason, they're doing a full backup, right? Not an incremental backup. But come Monday morning, if the backup isn't finished, I still need to get my production going, right? At that point in time, you can actually set up the bandwidth to drop it to 2 gig. The backup goes on, but doesn't significantly impact the production, right?
Anybody here using priority optimization to any chance?
So again, the enforcement is and the numbers, you can change them and they take place immediately, right? I mean, it doesn't have built-up time or anything like that. The other piece that we sort of took the notion of over-committing or over-provisioning and we applied it to quality of service. So imagine an array that has 120,000 IOPS and it's configured to be able to deliver 120,000 IOPS. Okay. Now, you could go carefully and sort of break up, everybody gets 10,000 IOPS, and then, you have 12 apps, and you get 120,000 IOPS, right? But that means that you're limiting everybody to 10,000 IOPS, and that may not be what you really want to do. So we create this notion of create a tenant and give that tenant a 20,000 IOP limit, okay? But if the tenant has multiple applications, the tenant could choose to give 10,000 IOPS to each one of its applications, okay? So obviously, 3 10,000s, 30,000 doesn't add up to 20,000. It's more than 30,000, right? More than 20,000. What this really means that a given application can go up to 10,000. And if one application is currently silent and it's not really working, the two applications combined can go to 20,000. But if that particular tenant decides that he wants to run all his applications at the same time, the combined IOPS from all those 3 applications can't exceed 20,000, because that's what the system administrator assigned to that system, right? So the beauty of this model is that a given tenant that has applications that run, for instance, at different time zones, at different times, right, can actually apply these application settings of 10,000 to each one of these applications, knowing fully well that it's limited to 20,000 IOPS. But because they don't run at the same time, it can give 10,000 to each, okay? Or you could actually say, well, I don't really know what my application is going to do. It's running all the time, so I'm going to give them, 150% of what I actually combined can get, right? And then let the applications fight out. And the very important application or tenant that chose to get 100,000 IOPS, he has one key application. It's his data warehouse. He just has to run. Doesn't, there is no ifs or ands or buts. He just gets 100,000, assigns 100,000, and by God, that's what he gets all the time, right?
I'm curious, what's the behavior of the system in tenant 1 if all 3 applications try to spin up and the system starts throttling it down? Will it allow an approximately even number of IOPS to each of the 3 apps, or does app 1 and 2 go full speed after?
Right. So the way it works, you actually start to the way the system starts to actually throttle, it throttles the guy who's the chattiest.
Okay.
Okay. So in practice, it means that if all of them are trying to do the 10,000, in practice, when you look at it statistically, they ends up being all about 7,000 each, right? But if it happens that one of them is super chatty and the other ones are not, so for instance, these guys are running at, let's say 6,000 or something, and this guy is really trying to run at 10,000, he will get throttled more than the other guys.
Okay.
So they will get the 6,000, and he'll probably get, whatever, 7,000, 7,500 or whatever, right?
Okay.
He will get hampered more, but that's just the behavior of the box. It tries to slow down the chattiest,
Okay.
member of the set, right? Because remember, this application could be made up of 10 LUNs, and of the 10 LUNs, a given LUN may actually be particularly chatty compared to the other LUNs, right? So the chattiest LUN actually gets the most throttle, right? Just because he's the one that shows up on the map more often than anybody else.
Okay.
Yes.
So IOPS and bandwidth are great. Is there anything that you can do to provide priority optimization for latency?
That's a very good question. A lot of customers actually ask the exact same question. It's like, hey, I'm not really monitoring, IOPS and bandwidth. I don't care. Latency is everything I care about. It turns out that I have to go back a whole bunch of slides. But if you look at the actual curve of latency, when we go up into IOPS, latency starts to go up, right? And really, what IOPS on a system are really, they're a corollary to the latency, because as the IOPS go up, you run out of resources to actually maintain the lower to low latency. So to go back to this question, the combined number is 120,000 IOPS here. Let's assume that the system had enough SSDs, right, to actually maintain the sub-600 microsecond latency at 120,000 IOPS. By limiting this stuff to 120,000 IOPS, essentially you're guaranteeing the latency.
Everybody will get
the lower latency that you were talking about, right? Now, it turns out that if this guy tried to go over 20,000 over and over again, because essentially he built his queue as deep as he can, he will see higher latency. We have to actually throttle. Throttling means adding latency to its workload, right? But that is a case of a workload that is ill-designed. And a well-designed, application tends to, when you're sort of starting to actually throttle it, it behaves to that throttling and issue fewer commands. But if the application is ill-designed and we just build up the queue of 1,000, okay, guess what? That means latency, right? So it
that
just
won't necessarily affect the other tenants' latency.
that's the whole point. The whole point is that it does not impact the application that matters, that is very latency sensitive. The latency that we introduced in order to throttle these guys means that this guy will actually go through unimpeded, and that's kind of the whole point. And in fact, it's not depicted here. One of the things that we added was the case where, I have a really, really big system with thousands of LUNs. I don't want to go worry about each individual LUNs and, how much this guy gets, how much that guy gets. I just know that these two applications are really, really important, and I want lots and lots of IOPS set aside for these guys. So we added this notion of an application, and then you have all others. So you can define two important applications, each one getting 100,000 IOPS each, and then an all others category that gets 20,000. Everything that is not defined, is not a group, all these guys just get one priority optimization group, combined together, and they get 20,000 IOPS. And that's sort of, you solve that problem of sort of guaranteeing a latency and IOPS for the two golden applications, and not worrying about individually divvying up, right, and acting as the creditor for every single one of those LUNs. All right. Anything else on priority optimization? We have a lot more for priority optimization coming, but this is kind of the current instantiation as shipping today. So this is sort of the overall changes that we have made. Sort of this is a normal thing guarantee that we provide to a lot of customers, and this is borne out over and over by customers that use thin provisioning. They actually use a lot less space than they anticipated. They always, and this is sort of a battle between the database guy and the storage guy. The database guy says, I want 2 terabytes, always, right? And the storage guy says, well, we do really need it, and now you don't really have to think about it. You just hand them the 2 terabytes, and often you realize they don't use more than a few hundred gigabytes. I don't know what your experience made is, but
depends on, again,
right.
in my early days of 3PAR, started with 3PAR in 2006, and it really comes down to knowing the behavior of the application. So in the DB example, we use a lot of MySQL, and when you do an alter table on a big table in MySQL, it will rewrite the entire table out on the disk, and it'll blow out a lot of your storage stuff. So when my last DBA came to me and said, I want 400 gigs for every DB, I said, okay, that's fine, I'll give him 400 gigs, and after 8 months or so, most of the ones are at 400 gigs, even though the DB is only 80 or 90 gigs in size. And he said, oh, I can't reclaim any, I can't give you back any space. So I'm like, well, you're going to pay for it then.
Yeah, it's all over the place. I mean, we have customers that actually were swearing in that they're at 80% efficiency, and then when they started rolled out in provisioning, they were at 30% efficiency. They actually went down to 30%. Right? And then
down at 9%.
yeah, I mean, but the other piece is that what's even more interesting. It's not that okay. At some point you use the space, but the initial capital outlay is a lot less, and that's really an important factor. The initial capital outlay.
I have our VAR was asking me, you know, how much do we pay for storage for our 3PAR versus how much do you pay like in the cloud storage? And it was a very complicated question to answer because, for example, in the cloud storage, you can't, in this particular cloud storage, you can't make a snapshot of a full volume copy. And I did some analysis with thin provisioning. For example, our company is a very small company, so we have 18 terabytes of usable capacity on our primary array. And I told them, well, with all the snapshots, and we're using snapshots, we have 25 DBs at least that run exclusively off of snapshots. And I told them, there's 120 terabytes that this small box is exposing. Go quote that from the cloud. And you take the read-only snapshot on top of that, it explodes to 220 terabytes that this one little box is exporting. And it's like, you can't compare the two.
So we talked about the fact that we actually have now, the other nice thing we actually didn't quite cover was the uniform flashware. Because we do have now this notion of every single drive. So today, a typical storage device usually has one hot spare drive set aside. So when a drive fails, you reconstruct that drive. We don't do that. What we do is we take a percentage of each drive set aside as what we call our spare media pool. Okay? So the nice thing about that is that every single drive is being written to all the time. You don't have a drive, in the SSD world, you don't have a drive that's sitting aside idle, not doing anything, and all the wear is targeted at sort of the neighbors next door. All the drives are getting the wear. And if a drive fails for mechanical reasons or for electronic reasons, right, when we are rewriting and actually populating the data, we are actually putting the replacement data on all the accompanying drives in the system. It makes for much faster rebuild time, but it actually makes for a much better wear leveling across the entire system, right? So you get much better wear. So the other technique that everybody uses in the SSD world, the way they actually get obviously you can get a lot more than 5,000 write cycles on a drive is because they put aside a whole lot of cells. They don't expose it to you. They tell you, it's a 400 gig drive, but it's really, got 800 gig worth of cells or 600 gig worth of cells depending on SLC versus MLC versus the over provisioning they do. Because you're setting spare pools aside, it is also a form of, setting aside some cells that are not being written. So essentially, and because of the way the grow works for us, imagine if this is a drive, right? And these are the chunklets in a drive. When we are actually adding volumes, we added it to all of them. All this is a spare pool that is not being written that can be actually used for wear leveling by the drive underneath, right? And as we are growing the space on these drives, there's less space available, but initially you had a lot of wear leveling, so it actually extends the life of the drive quite well, right? And so now we talked about proactive management. This is the case where all these drives have wear gauge. We monitor the wear gauge, and then we generate. There's two ways we do it. We send them all back all the time to HP, so we can actually monitor and actually have the statistical data in terms of what the wear gauge layout, what the wear out is, and if the current algorithms are working well. So that sort of helps us with development. But beyond it, with the customers, when it gets to about 95%, 90% wear, we generate an alert. I don't know what the number actually is. Is it 90%? I think.
Yeah, it's 95%.
Yeah.
The alert started 90%.
Okay.
Yeah, 90%.
We warn at 90%. At 95%, it becomes something that says, okay, you need to take action. You need to actually service that magazine and service that drive and replace it with the replacement drive. And, we don't really anticipate getting there, with the current generation of drives. They just have a lot more over provisioning that is required for them to actually.
You still require 4 gigabytes per second of bandwidth, right? That is the best case scenario. And if your array is topping out at 2.2, 2.3 gigabytes per second, you're not really doing a million
correct statement to make. So this is hugely important. I always try to point that out. A number of customers, when we're working on the all-flash array, they're always interested in the scalability. So how many fiber channel ports do you have, for example, right? And guess what? This model, if you look at the hardware from the outside, it looks exactly like the 7000 model. So it has 24 fiber channel ports, like the other 7000 models have, right? So hugely important from a host connectivity standpoint. And the best thing about, and which we'll cover later, is of course every single data service that we have available in the 7000 or on the 10,000, right, is available on this platform from day one. Right? And you don't have to wait. We want copies, snapshots, encryption, peer persistence, which we will cover. Everything is available on this all-flash array from day one.
The thing that's interesting from a connectivity perspective, we had a couple of customers tell us, right? We had some array vendors that were doing iSCSI only. We had some that did not support AIX, right? So I think this notion of fiber channel switches, HPAs, fabrics, that connectivity matrix, it's not something you build in 2 months, right? That takes multiple years, not something to trivialize.
One of our first all-flash arrays, 450 customers, is an OpenVMS customer for that matter. How many arrays are out there in the market all-flash that support OpenVMS? Very few actually. So it's kind of amazing.
And a lot of all-flash arrays using InfiniBand as an interface. Do you see that coming down the pike here?
So I think something Siamak mentioned. There are opportunities to reduce the latency, right, at every stack. And you were making the point that you're already at 200 microseconds. How low can you go? Zero is up pretty fast, right? So using InfiniBand is maybe one option, but there are other options. For example, going to NVMe directly. So we are already, without InfiniBand, we are already at 200, 250 microseconds in terms of write latency. Right? Without
Yeah. So just to be clear, the number at 700 microsecond, that is at the peak.
At the peak.
500,000. If you sort of just drop this at 100,000, you're saying 300 microsecond latencies, right? So this is sort of at the point where the curve starts to go up, right? So if you just go back a tiny bit, you will drop down to 300 microsecond latency, right? And this is, by the way, all the way from the drive. So to be clear, these numbers are all cache misses, right? This is through and through. If I just am going to the cache, the numbers are about 100 microsecond, right? If I happen to get lucky and hit the cache, right?
And these are all distributed volume numbers, so we're not doing those tiny little tricks where every volume is laid out exactly behind one controller or a pair of controllers.
Yeah, and you can actually see that here, right? I mean, if you sort of naively look at this at 3.2, why is this not 6.4? The answer is we don't play tricks and actually send the I/O to individual controllers that are owned by that controller. These are true distributed volumes, right? And so there is a bit of a loss of throughput, and we actually use true distributed volume through and through all the way to the disk.
Okay, yeah, and one thing I learned about this is, and which referred to about this is this stuff, 96 terabyte. It is already one of the largest capacity that is supported. I mean, there are some that go higher, but the good thing about our approach is we're going to be working on 1 terabyte drives, 2 terabyte drives, SSD drives, right? And nothing stops us from supporting 240 times whatever the capacity of drive that we support. Right? It's just seamless. Our 7000 series already support 800 terabytes actually, right? And this is built on the exact same model. So theoretically, we can support up to that much today, and then so okay. Just keep moving. So from a there are two ways you can look at an all-flash array, right? One is your performance configuration, where you're using an all-flash array to drive down the latency to the last bit of microsecond that you can drive down to, and get the IOPS to the best possible, right? So really dense, compact configurations, right? And you can just get from a node pair, you can get over 250,000 IOPS at less than like at 700 microseconds, and just 4 controllers. This is 2U, by the way, and this is 4U, right? So such dense and compact, 4U, 4 controllers, 48 SSDs, and get over.
I'm curious if you have a slide comparing what 10,800 and 500,000 IOPS with SSDs. How much space, 4U for the 7454 node, and how many for the 10,800?
Okay, I can actually answer that. Okay. So 10,800, it is meant for scale,
yeah,
right?
Yeah.
A lot of drives and all that stuff. But 10800, you would say 28 U easily just for the controllers, and then you at least add the one JBOD. So it goes 32 U, 36 U.
I mean, if you have 8 controllers, it means you have to have 8 drive pages, right?
Yeah, at the least. I mean, I'm talking only just 2. Yeah. So that will go much beyond that, right?
Yeah.
Whereas this guy can get you there in terms of performance and latency in 4 U's.
Yeah.
Right. So, so now, so there are customers who really, want the performance, right? But they also have to lay out their data. One of the customers that we regularly talked to when we were designing this all-flash array systems, he was constantly giving feedback that, yeah, I get the performance, but really what I want is I have this 20 terabyte, it's not just one database, multiple databases that I need to run on, right? And it's not just the IOPS, I want consistent latency across that 20 terabytes, right? Now, how do you get consistent latency? The way you lay out your data, you populate your array with as many SSDs as you require to lay that data out. The good thing about SSDs is that every single IO is going to get 300 microseconds of latency, right? And that's huge. So even in this 96 terabyte configuration that I have over here, you drive it to 500,000 IOPS, you still get 700 microseconds of latency at most, right? Much will be more of your IOs will be much lower than 700 microseconds. So that's kind of the other use case where you have lots of data and lots of capacity requirements, and you still don't want to mess with your latency. Okay, so kind of very two distinct use cases. And if you look at the industry, the all-flash array industry, there are some players who are really just focused over here. Right? And I was asked this question by one of the bloggers, one of my, when we were doing Discover actually, okay, is this array focused on the performance-sensitive market or really the mid-range all-flash market, right? Because there are many players who are really over here, right? And there are many more players who are in this. And the real answer is, God, come on, this one array is focused on both of those segments, right? I mean, if you're a customer for whom performance and density is important, this configuration. If you're a customer for whom consistent latency, lots of terabytes are important, there you go. Right. Okay. A little bit about the tier 1 resiliency and the software features that I just described at the outset. So it's interesting because when you look at a number of all-flash arrays in the market, okay, there's one vector, and possibly two, where they have really optimized upon. One vector is, of course, performance. So all-flash array, by definition, they have optimized on performance. And the second vector is really, some kind of a data efficiency story, right? So some kind of compaction, G2, thin, whatever story, right? I think most, if not all of them, forgot that if there's a customer who is going to spend hundreds of thousands of dollars putting their data on an all-flash array, getting the speed, that data is important by definition for that customer. So they want, one of the analysts told, the IOPS on an array that is down is 0.
Right. And how fast it will matter.
Right? So it kind of puts this in perspective, right? I mean, you do all these beautiful things, but then your array is down. How good is that array, or whatever money you spent, right? This is why these persistent technologies that thankfully 3PAR has already is important on an all-flash array, right? So persistent cache, for example, allows you that even in case of a controller failure, first of all, nearly all all-flash arrays today are dual controller design, right? And there are some scalar designs, to be honest, but nearly all of them are dual controller design. Four controller design means that something happens to one of your controllers, you're doing an upgrade or it fails or whatever, you don't go into write-through mode. Right? You still maintain your cache coherency. Right? Very important from an application performance standpoint. Right? Persistent ports, something that we discussed in the previous session. Today, it allows us to do online firmware and software upgrades without any dependency on a multi-pathing software. Right? That it does today. Right? In future, the way our implementation is, it will detect laser loss. Right? So something happens. I mean, that is by far the most common, case why customers need this kind of a technology. That someone just pulled the cable or the cable got pulled out. Some maintenance guy who was doing something didn't know which cable to pull and the wrong cable got pulled out. Okay. In future, in the near future, we are going to actually detect that across a laser and just manage using NPIV. The host will not even know the IOs which were going to a particular port will automatically go to a partner port, right? With persistent ports, right? So that's really a near future. Now, peer persistence, we're going to talk about this in a little bit detail. This is really the peer persistence does two things. It's an intersection between our federation story and our disaster recovery and HA story. Right? So it's kind of, that's why I thought we'll talk about this a little bit more in detail right here. So what peer persistence is, in a very simple terms, is the capability to automatically fail over from one array to another array, right? That's what it is. Another interesting thing over there is it is transparent to the host. So the failover is happening at the array level. Array is failing over from one to another, and it is completely transparent to the host over here, right? And the case that I have depicted right now is a case where your entire data center has failed. Okay, the entire data center has failed, which means your VMs that were running on this side of the house have migrated thanks to clustering software at the host level, and your array that has failed over to the second array. All of this has happened without the host actually knowing what has happened or the application getting any downtime for whatever reason. Okay, so we'll get into a little bit more detail into that. Okay, so what's happened? A couple of things that I want to point out over here. First, we are doing it completely natively within the array, completely natively. To draw a parallel, there are products out in the market which enable this kind of a capability, but they only do it when they have some kind of a appliance over there, okay, which then adds that additional complexity to manage that appliance, and that appliance is really what is managing the failover from one to another. Okay, in 3-part, you can do it natively between any pair of 3-part arrays. You can have a 10,000 over here and do this to a 7200. You can run a 3450, you're all flash, and you can run a 7200 over here, and then this capability will work natively without any need of an additional appliance. Okay, so that's the cool part that sometimes sort of I forget to mention. I should correct. Okay, now the additional point. So we have offered 3-part remote copy for years, right? And more than half of our customers really use remote copy today. Okay, and when they want to use peer persistence, all they need to do is to go to those remote copy volumes and just enable peer persistence on those. It's almost as similar. Try this persistence. As simple as going to remote copy volumes and saying, I want peer persistence in these volumes, and those volumes get enabled with peer persistence. That is how well integrated this new technology is for our existing customers. Okay, and you can't get this unless you really build this from day one. Okay, so this is of course it works across all 3-parts I already covered, and now with the June release, we also got it VMware VMSC certification of this technology. That was required for a number of our customers. So we already covered that, and it is available on all 3-parts clearly because it's based on the OS, and the same OS runs across the platform, right? So it's VMSC certified.
And VMC today is Store Virtual, NetApp, and 3-part, right? Are these the only 3 that are VMSC certified? Do you know?
No, VMSC is on our HP side.
No, I'm talking about in the industry.
Competitors,
the others?
No, the competitors, the only thing they have is the vPlex.
Yeah, that's exactly.
That's not a disk array.
Right.
Yes and no, right? I mean,
so if you pull out a VNX or a VSP or a VMAX, etc., none of those, and anyone is welcome to go to the VMSC certification site and actually see specifically which arrays are supported.
Right. Exactly. Yeah. Okay, let's get into a little bit detail over here, right? Because this is kind of interesting for a number of our customers. So what I have over here is 2 arrays, 2 3-part arrays, and how peer persistence is laid out. So the first important thing that we do to lay out peer persistent configuration is you see these volumes over here. So in a classical remote copy configuration, I'll have a primary volume that will be sitting on this array, right, and it will be replicated to a secondary volume on a different array. Right? That's classical remote copy synchronous configuration. And similarly, you'll have a primary volume over here that's replicating back to this array. Right? So both the arrays are running in an active mode. They're not running in an active passive, right? Because both the arrays are being used as active arrays. Now, in pure persistence configuration, what we do is both of these volumes, which are one is a primary, one is a secondary, both of them are given the same worldwide name. Right? That's kind of one of the most important tricks that we do, and we use a Lua. So both of these volumes are given the same worldwide name. So the question is, okay, so when the host is doing I/O, how does it know which volume is the right volume, right? Like, are you just confusing the host, right? So that is where we use a Lua to make path to one volume as active and path to another volume as standby. So the host, when it sees volumes, same worldwide name, but only one path is active. So all the I/Os are by definition going to this just one volume. Okay. Now here's the trick. When you do a failover or a switchover, really in this case, all we have to do is just switch the paths from active, which was standby, to active. That's it. There's nothing else. We don't, because these are already in synchronous applications, so the volume is already in sync. Right? There's nothing that we have to do at that point in time. We simply made the paths, from. Okay, so this is just a representation. We simply make the paths from. This path became standby. This path became active, and all we did was just reverse the replication relations. That's about it, right? So this is, this is just so simple to implement, right? Works on top of synchronous remote copy that our customers have been using for years now, okay? And just so easy to manage actually, right? And one of the things that we have done with our June launch is now we have a arbitrator. We call it quorum witness, right? So this what is this quorum witness doing? The quorum witness is third person, if you will, is just sitting over there, monitoring both the arrays, right? Monitoring the replication relationship, monitoring whether the arrays are active or not, and if there is a possible chance that if there's a scenario where this array is out, or the data center is out, or some true disaster happens, the quorum witness recognizes that and automates the switch over from this array to this array. Right? That's what the quorum witness is. So you sort of taken the manual element out of this complete configuration by having this third person who is just sitting there and monitoring, just polling the arrays sometimes, and just making sure that everything is working hunky-dory.
So CD, is it tied into SRM or
so yes.
This is kind of aside from SRM, right?
So it's actually yes and yes to both the questions actually, right? Because it is tied into the SRM in the sense that you can actually run SRM if you want in conjunction with pure persistence. The way we see customers using that capability is that you've got pure persistence between these two arrays, and you've got a third array somewhere which you're doing an asynchronous replication to, and then you have SRM between the secondary and the third array, the tertiary array, right? And yes to your second question, because they are separate. Pure persistence and SRM is not like competing, or they're almost orthogonal to each other, right? But they work together beautifully.
Yeah, I mean the best way to think about it, in the SRM world there are two VM instances, and they have a failover partnership, okay? And the entire system, VM or subsystem, knows about the existence of these VMs, and so it coordinates, and then it understands the VM dependencies that these VMs have to come up at the same time in this order, right? This is the case that from a VM perspective, this entire world has a single VM instance that happens to be hosted on LUN. That LUN happens to be read-write or standby on one of these two arrays. But so this is one single VMware system, right? And therefore there's a single vSphere instance that controls this, and there's a single VM instance, right? And so as PD pointed out, if you lay over SRM over this, there will be a third array at the disaster site with a copy of the LUNs, right? That will come from one of these arrays, right? In an SLD configuration, what we call an SLD configuration, right? And then in that world, if this entire thing fails, right? These two arrays and these two sites fail, then the SRM engages and brings it up, right? But in the absence of a total failure of both sides, right? SRM doesn't do anything. So it's unlikely to configure
And the
something like
fabric
that.
has to span both sides.
This is what we call a uniform. Right. So there are two, in the VMSC world, there's two ways to do it. There's a uniform and non-uniform way. you're supporting uniform configuration. In other words, that the fabric spans the entire thing. And remember, these two arrays are connected through something that is fabric latency and fabric, throughput. So obviously these two are on the same fabric. So when the two arrays are on a fabric to support the remote copy, that same fabric is then available to the host in this world where the hosts are also on the same fabric.
So the fabric we use for the synchronous copy as well as the host access.
That's correct.
Right. Solid C. Yeah.
Yeah.
So where does the quorum witness live or exist? Where does
Right. So the quorum witness by design must live on a third site. Remember, it is acting as the tiebreaker. In other words, if a communication loss occurs between the two arrays, okay, what you don't know is if a site has failed. Let's say this array and this array are talking, right, and a communication loss occurs. The question is, did the site go down? Did I lose communication with the other site because that site, or did my site's network go out and therefore I can't talk to the outside world? So you don't really know what the right answer is. You just lost communication. If you have the quorum witness and it's the site, so the best way to think about it, this lives in a world where it's a client of the actual apps up there. So imagine if your apps are providing services to the outside world. This thing lives in the outside world that the I/O services are needed from, right? So it's communicating with both arrays, right, and receiving heartbeats, right? So if a communication loss is detected from this array, and a communication loss has occurred from the quorum witness to this array, okay, you can either assume that either the entire site is down or the entire networking infrastructure is down, and it can't provide services to the rest of the world. That's a key point, right? That it cannot provide services to the outside world, right? Either because it's down or because its networking services went away. That's when the two of them together, they have two votes and they decide that they can take over I/O services. They essentially insulate the world and then bring up the I/O services, and then so the way it works is that because the way VMware works and they have an HA configuration, these guys are monitoring heartbeats of the VMs. And so what happens is that the heartbeats go away, okay, and then they start to actually bring up the VMs over here. If the VM was actually hosted there. If the VM was hosted here, just there will be a failover of the VMware DMP, and so the VMs continue to run. So depending on where the VM was hosted, there may be a VM restart due to heartbeat loss, or there may be just a path failover. The VM continues to run. Maybe a momentary pause in I/O when the path failover is taking place.
So I guess what I'm still wondering is where does it live? Is it a service that's provided as part of what used to be stats, or is it a machine that I have to have running somewhere outside of the cluster?
It's a VM that you deploy outside, someplace in a third site. And all it needs is, it runs a web server essentially, right? And these guys are essentially talking to the web services interfaces to it. So these guys are continuously sending heartbeats, and they continuously ask for it, what heartbeats have you seen, right?
Okay.
So you're sending heartbeats, receiving heartbeats, right? And then it acts, so it doesn't really actively do anything other than act as a communication channel through a third site. That's the best way to think about it, is a backup communication channel going through a third site, and that's the key
Right.
point, that where the data services needs to be provided within your entire infrastructure.
Okay.
That makes
So that
sense?
means that the service controllers or wherever this is heartbeating to has to have external access of some sort.
Yeah, okay, so the service processor on communicating with the quorum witness. The arrays are directly connecting to the quorum witness. So if you're asking a security question, the arrays need to have web access, right? Essentially HTTP access, right? To the quorum witness. Now you
Okay,
need to set up
not
your
the other
firewall
way
rules
around.
that there's outbound, not inbound. That's the key
Okay.
point. Outbound access to the quorum witness only, not inbound access.
Okay, thank you.
So is it using SSL?
It is using HTTPS. It does not use HTTPS. The reason we specifically chose HTTPS because people are very comfortable with that particular protocol, and there's lots of monitoring software that can deal with that relatively same way.
I'm curious, does it support the use of proxies? So if you have to if the array needs to talk externally through a proxy inside?
You cannot configure a proxy.
Okay.
But if you can configure a proxy transparently, right?
Okay, yeah.
Then we will support it because it's transparent to us. But
Okay.
the typical configuration of configuring a proxy server is not supported.
Okay.
For clarity, the quorum witness, you say, has to reside on another system out of that.
Yes.
That'd be another 3 3-part system?
No, it's a VM.
It's a VM, so it could be
So
on
it could be on anything.
Reliant
It
somewhere.
could be
Yeah.
exactly. It could be a Reliant server.
Yeah.
It sits on a third side, right? The VM could be hosted on a 3-part device, right? I mean, that. But it's just a VM as far. In fact, what we ship is an OVF. It's open, OVF file format. So you could initially we were only supporting in VMware, but because of the way it's packaged, it could be in a Hyper-V environment or KVM environment because of OVF file format, right? But initially, for support reasons, we are only deploying it on. We're supporting the deployment on the VMware only, but the actual packaging is OVF.
Thank you.
Okay, great. So, yeah, we just keep moving over here. So, we talked about 3 vectors now, okay? Super, thank you. We talked about 3 vectors now, okay? We could talk about performance and efficiency, right? We talked about the data resiliency. 4th vector, in our mind, to be successful in an all-flash array world, right? You need to execute on 4 vectors truly, okay? Performance, efficiency, data resiliency, and the data mobility vector, okay? Because guess what? Your data that is there on flash today will age. 6 months, a year, 2 years, whatever your time frame is, that data will age on all flash. And now you will have need to move that data around to a lower tier, cost basically. Unless you have all the money in the world and you can just keep throwing flash over and over again, right? And nobody had it, right? So this
John
day.
Inventor does.
There are very few like him. Okay.
That's right.
So this is why this becomes key, right? Because so you start with you're hosting your data on all flash, right? But what do you do once the data ages? Not only that, actually, for service providers, they actually are making this as an offered service now, because they're going to their customers and saying, if it is Cyber Monday and you have 2 applications that require all the performance that you can get, I can actually move that workload from wherever I was hosting onto the all-flash array, right? And for that one day or those 4 days, starting Black Friday, Cyber Monday, your application performance is just on all-flash, right? And after that, I'll just move it to you, and you can pay me only for those 4 days, right? So this is central to using an all-flash array now, right? So this is why, and this is right now with Peer Motion, you can just move workloads around as we deliver more and more on our federation story, right? We deliver workload balancing, right, or federated provisioning. Imagine, a case where some application is becoming hot and it is running on an HDD, and you can transparently and seamlessly just move that application onto all-flash, right?
Based on a policy, right?
Based on a policy, right? So this is the 4th vector on this vector only 3-part is able to execute today. I mean, there are a number of players out in the market, and we'll get into the competitive.
Well, I guess you could put a mix of different array types, and you could use
Sure.
an SVC or something else, maybe host space. I guess you could put something together, but the question is at what cost and what complexity.
Okay, so let's get into this is, by the way, this is a use case from a service provider. They educated us about this use case as to how they will use an all-flash array.
Want me to present this?
Yeah.
Okay. So let me talk about this slide. So the service provider has today 4 tiers of storage within this large array, right? They've told us that the most cost-effective way to run storage as a service, shared storage as a service, for multiple tenants is to use a large array that's shared, right? That way you can get the economies of scale. So 4 tiers, right? 80% of their revenues come from the middle 2 tiers. Okay? And so they have 10% here, 10% here at the bottom, right? So what they want to be able to do is say, okay, for the top 10%, first of all, I want to be able to offer them yet even a higher level of service. Okay? So I want to be able to say, okay, here, you're running on, let's use United Airlines, right? You're running an Economy Plus here. Let me get you to business or first class. Okay? And use priority optimization to get you to first class if you like. And from a service provider perspective, they want to charge for it. Right? That's a revenue opportunity for them. Take the bottom tier now. You can say, okay, it's a customer now with adaptive optimization software. I can tell that your cold tier is really cold. It's freezing cold. You're not even accessing it, right? well, let's move this to a lower cost array, okay, and we'll lower our service price to you, right? Or I've got a service level to maintain as a service provider. I'm going to maintain that price I charge the customer, and then I'm going to, take this to my bottom line by lowering my cost. Right? So I think it's very interesting when you start thinking about, the ability to view federation in this context, right?
I'm curious, how do you see the future of the arrays that are classified as scale now that you slash the cost point of the three-part platform,
Right.
and you also have introduced this new high-speed tier.
So the question is, does this become obsolete, right?
Yeah.
And I think it depends on the really large service providers, the bandwidth, the capacity, the ports. I think you're going to find that that's still a need for this, right? But there's going to be some places where this and this are sufficient, right? In fact, that same service provider said, hey, I have a similar setup in a different part of the world where the bases are a lot smaller, and I want to use a 7400 here, 7450 here, a 7200, right? Or a 7400 with flash, a 7400 with spinning, a 7200 with spinning. So I think you have those choice points, right? Given the flexibility of the architecture, and I would size it to that. I don't think it'll go away. I think it'll just sort of
Shrink.
segment the markets,
Okay.
right? Maybe depending.
I'm curious from a port expandability standpoint, the mid-range three-part platform, even these most up-to-date ones from a port, I guess I should say from a PCI slot standpoint, there's not a lot of slots available. So if you install an ASIC HBA, you remove a lot of capacity for FC ports, for example. You guys foresee yourselves in the future expanding the mid-range controller so you have more PCI slots available?
So you could solve that problem by expanding the mid-range controller, or you could solve the same problem by actually taking these guys and making them compact, so they look a little bit closer to this, but they don't lose the port counts.
Okay.
Right? So instead of going from elevating the mid-range higher, why don't we just take these higher-end guys and just shrink them a little?
That would be fine too.
That would be fine too,
Yeah,
right? So
yeah.
that's kind of the project we are taking.
Okay.
All worlds will collide here at some point.
So the peer motion today is a command-oriented facility, but you believe policy management will come to automatically move?
So today, peer motion is also now available on the GUI, correct?
Yeah, it's available on GUI.
But today, you're right, it is sort of manual today, right?
Yeah,
It's a manually driven step. But yeah, I think policy is the next step, right?
So adaptive optimization actually examines data heat per se on a periodic basis, and then moves data from one tier to another, right?
Right, region IO density. That's
Yeah,
what
you see something like that operating at the peer motion level as well?
that's the policy-based workload
Yeah,
balance.
so this is beyond the year. We're not supposed to talk about stuff beyond the year, but we'll sort of, if you think about it, there's this notion of virtual center in a VMware world, right? And then when a virtual center exists, and you have, let's say, is 8-node VMware cluster, what do? We add a 9th cluster, 9th host to it. And if you happen to have, 100 virtual machines, it says, oh, a brand new host showed up. What do I do? Figure out which ones that actually, there's a policy set of decisions to be made by DRS. We've set up a bunch of questions about what priorities I need, what SRIV rules are, what is attached to it. But then it makes a decision and says, I'm going to move these 5 VMs from these 5 hosts into the single host that just showed up, right? Imagine a world just like that, where there's an external system that you sit in front of, right? You'll be integrated with our GUI, right? And a new array shows up on your floor. You'll examine the map of the fabric. What hosts are attached to what arrays are attached to what is the disaster recovery configuration of this array versus these other arrays that just showed up, and say, these nuns can move from here to here. Initially, it would be a suggestion, and then you can imagine a case where a policy can be applied that says these nuns can move from midnight to 6 a.m., right? And the system will do a policy decision of, okay, I'll apply these optimizations at midnight. And then you have to take into account, I'm coming from an array that has an FC drives, and this needs to have an FC drives, right? Or it's attached to the right fabric. All those decisions have to be
But doing that on a periodic basis when a new array arrives is one thing.
Right.
Doing that on a daily basis or every shift basis and moving volumes around, potentially terabytes of data,
Exactly.
is a different discussion altogether.
Willy-nilly, exactly.
Right.
But there's a case to be made. There's a use case where the load pattern shifts significantly over time, right? At that point in time, what is your recourse, right? Moving the data. So
So the question is, how much of that stuff do you want to leave manually, or have the system suggest and then you take action? But at what point do you become comfortable enough for the system to say, you take action, right? And remember, moving terabytes of data is a big deal, but if you have SSDs, you have lots of bandwidth. You can move those things pretty darn fast, right? Without necessarily impacting the box.
And I think the other thing to think about is unpredictability, right? That's the problem you're trying to solve, right? How do you respond to a spike?
But you're right, it's a big deal. Moving a vMotioning a virtual machine is very different than storage vMotioning the LUN underneath it. The vMotion gets done all the time. Storage vMotion almost always happens as a result of lack of capacity or rebalancing or whatever, right? It doesn't happen as a reaction to load, right? But you can imagine, as you create more and more bandwidth in these guys, and the backends become much more.
Some of those are SSDs, some of those are best only. I mean,
That's right.
So there's a challenge moving.
Absolutely.
Yes.
Yeah, that's right. That's right.
And an application today,
That's right.
is easily made up of 10 LUNs, each about 200 gig in size. You're talking 2 terabyte of space.
Right.
It's a non-trivial amount of data to move, and you just don't do that until you have a really really good reason.
Correct. I think the operational considerations are going to be equally as important as the technology considerations. Right? Okay, let's keep going.
Get on to the it's amazing. We do such a bad job of marketing. Our vice president said we call this as a base OS. Turns out our base OS is not really just base OS. It has too many things inside of it, actually, right? So, everything that you see in the slide right now is available on 7450 all the all-flash array today. It was available day one, right? Base OS, which we call, it has things like persistent ports, persistent cache, autonomic groups. Thin provisioning is part of the base OS already, okay? System tuner, I mean, it's amazing the kind of feature and function that we have built, and that we just dumbly call it as base OS, right?
Well, yeah, I mean, in a lot of cases, even stuff that are not part of the base OS, it's still there. It's just a key. You have to type in a key to turn it on.
To turn it on.
Yeah.
That's true. Yeah. So, but
And that's a good thing, by the way.
Yeah.
No, install software.
Everything.
Although HP does often try to charge a professional services fee to install the key.
Let's put Vision for
to copy and paste that key in.
Hey, just to make you feel at home, we're going to charge you for lunch today, okay?
Appreciate it. That's expensive.
Way to go. Yeah. So outside of the base OS, right? So see the replication suite. Every single tier 1 that functionality that we offer on the 10,000 is right over here, actually, right? Data optimization, priority optimization is part of the data optimization suite, right? We've got a number of app suites, not to forget, right? So you want recovery manager, or what we now call application suite for VMware, allows you to take app consistent snapshots at your DR site, so that no matter God forbid something happens in your primary, you can bring up your application from an app consistent snapshot that you took using recovery manager for VMware or Hyper-V, Oracle, so on and so forth. Right? So every single thing, right? Okay. This is the part where I always believe, please educate me if there is something that is that you find has changed, because it's hard to keep up with spec sheets from competitors, right? But there are a couple of ways in which we look at our competitors in the all-flash market only, right? One way is to look at controller scalability and advanced data service, right? So competitors who offer multi-controller scalability, and competitors who offer advanced rich data services that we offer, right? And if you look at it, most designs currently are over here, actually, right? So and just to put it in perspective, going from a dual controller to a multi-controller is a non-trivial exercise, right? I mean, you have to think of a lot of things. Have people like Siamak working for 5 years to move from here to there, and market doesn't stay with you, that they move. So it's not. So my sort of assertion would be that competitors who are right now in this box, they're pretty much going to be in that box for a very long time. Okay, and going from here to here, right? So jumping on the advanced data services pool, that's a lot of multi-year software work that anybody has to do, including 3-bar, by the way. Okay, right?
So PD, you wouldn't say like the HDS VSP is an all-flash array because it doesn't just have a version that just supports all flash. I mean, they have a flash optimized system there.
Right. So my background is I was also the XP product manager. I've sort of made my bones in storage working on the XP product line. So it's like Siamak mentioned, it's a great box, right? But one of the fundamental things about being an all-flash array is around density. Okay, how much performance can you deliver in a 2U or a 4U box? Right? It is for the same reason why we don't say that the 10800 is a flash optimized box, even though it supports a number of SSDs and it can give you the IOPS that you can see on a 7450. You can get it from a 10800 as well, right? But you don't see us proclaiming that that's a flash optimized box, right? Because hey, the density, right, is not amenable to be called as all flash.
Yeah,
so
I mean, if you take a 10800 and put it in a colo, you may require 20 kilowatts of power hooked up to it,
right,
because you need those
right,
the 30 amp lines, even though it's not drawing as much power.
Right, exactly.
So I mean, it's
right. So IOPS per kilowatt. I actually have an interesting metric that I don't have it over here, but I can send it over. Number of IOPS that I can draw from every single watt that you use, right? In an all-flash array, at least in 7450, I can say it's in hundreds, whereas in an HDD-based traditional array, it is in kilowatts, right? So that's a significant difference. Okay, so and this is one way of look at this. The other way is to look at this is the way of data services, right? And
Can you go back to the
Oh, yeah,
I want
sure.
to make one point. I actually took a look at the EMC Extreme IO, just to do a quick look at their specs, the number of controllers they have, and how many IOPS they get per controller. And I actually encourage you to go look at it. It was actually quite surprising for an array that is just coming up, and it's preferred to be, all flash optimized, and it doesn't have any other data services. The number of IOPS that they get per CPU cycle is 1/4 of what we get. Just go look at the numbers, right? If you look at the number of socket cores, the number of sockets they have, they have to have 4 times as many sockets, right, to actually get the same number of IOPS that you're getting out of our system, right? That says something about just what I call IOPS per CPU cycle, right? It is significantly different. So these guys do actually quite well. I mean, Violin specifically does quite well on that scale of IOPS per CPU cycle. But the trap that they're in is that they've designed an all-integrated hardware system together where the CPUs and the memory modules are all integrated, and they'll have a challenge to ever go beyond 2 nodes, right? Because they're fundamentally create a PCIe fabric that connects the front end and the back end, right? And so they'll state it while their IOPS per CPU cycle is great, they're stuck in 2-node design. These guys, are multi-controller scalable, but their IOPS per CPU cycle is really horrendously low, right? You have the advantage of having great, IOPS per CPU cycle, but also the ability to actually scale beyond 2 controllers, right?
Beautiful point. Yeah, it's almost you can all. I was reading one of the comments at the register, and almost there was one very pertinent comment that it's not really all flash arrays, it's mostly all flash appliances. Okay, it kind of makes the point that you were making, right? Okay, so this is one way to look at this. Clearly, let's look at differently, right? There are customers who require these data services. These data services have evolved over the last decade for a reason, because customers actually deploy and pay for it, right? So I'm looking at very fundamental things that you expect from an array, right? And it's interesting. T10 diff support, we actually showed that to you when we were talking about adaptive read, when Siamak made a very small little comment that if the host IO is 4K, we actually read 4.2K because there are some extra bytes that we read for diff. Turns out diff is actually a pretty differentiating factor when you're talking about enterprise class of arrays, right? Why? If you don't have diff, you're not protected against silent data corruption. So you're doing all great performance, but turns out that the data got corrupted and your host didn't know about it, and you started returning bad data to your customers. How do you protect against it if you don't have diff, right? And for us, we actually get it off the bat because we've been supporting diff on the drives that we use for a while now. Okay, so that's one, right? QoS we covered, transparent failover, we covered that. Three-site replication. In one of the meetings, I got this comment. Why do you say three-site replication? You should have another row that said two-site replication, because a number of these guys don't even support that, or if they do, it's pretty limited support, right? So, right, three-site replication is something that we support on our Flash array day one, right? Encryption, yeah. So there are some, like for example, Violin recently made an announcement that they support encryption, and actually Pure made an announcement that they now support encryption. So I should update this slide, but encryption is pretty big, especially in the markets where all flash array is relevant. One of them is healthcare, okay, because they have the money, first of all, to pay for something like this, right? And secondly, they require the performance. I mean, they have, even without the all flash array, with some of our healthcare customers, we have service level agreements, right? The latency cannot go below a certain threshold, that there is an agreement. So they have the money and they have the need. Guess what? They also require the encryption capability. So works pretty good for us. Federation support, something that, just with three-part architecture, we are able to do this, whereas others are not able to, right? So if you look at the comparative picture from these two angles, right? Multi-controller scalability, advanced data services, we see that 3% 450 really stands apart. And thankfully, we've launched this array. So now is the time when actually our customers have started looking at this, and we are actually pretty pleased with the numbers that we are getting on the 7450. I mean, it hasn't been even a month since we've launched the array, and we're getting pretty thrilled with the number of customers.
So, Priyadarshi, on that replication, I think one thing important to identify there is that when you're replicating, your biggest limiter is typically what? Your link. So in the case of 3PAR, if you're replicating from a 7450, you have the capability of replicating over that slow link to an array that's all spindle. Because why would you put SSD on that other side anyway if your true limiter is going to be the link anyway? You don't need SSD on that other side. So not only do they not have the capability of doing replication in the first place, but once you actually decide to do replication, you're not going to be replicating over the link at the pace of I/O or bandwidth at which is being happening on the array. So you might as well have that going to another array that's actually all media. You have the capability of doing that to a high-end tier 1 array or to a mid-range array. So it's another piece of it.
Absolutely. It's interesting. If you put an all-flash array and your synchronous replication takes 2 milliseconds of response time, you've just thrown that money for no good reason, right?
You have to be careful because sometimes what you're solving is a read latency problem.
Okay. So
if the application is heavily read-based, it makes sense in that world to actually have SSDs locally, but not necessarily SSDs remotely. So it really depends on what problem you're trying to solve, right? In that case,
and you also need to make sure that, if you're going to switch over to that site, that it has enough
Yep.
IO capacity.
If you're doing active or trying to get there.
I think it'll be interesting to see what the difference you do local replication synchronous and then far asynchronous. There's going to be lots of variations with the flat array. I think we'll have to see some interesting variations to models, right? Operational models. Yeah.
So what's missing on the chart is a NetApp product, the F540, right?
So NetApp, where is NetApp? Okay, NetApp. So NetApp, 300,000 IOPS or 250? Is that?
I'm not sure, but
yeah.
I mean, it's got non-disruptive scalability.
Yeah,
It's got online
yeah.
updates.
Yep.
It's got replication capabilities.
Yeah. No, I was just making a comment. NetApp, the product that they just announced like a few months back.
Yeah.
It
EF540.
goes. We can look at the data on the website, but it doesn't even go beyond 300,000 IOPS. If you can remember well, actually.
Yeah,
I think that's the issue. And I think they've also announced another array coming next year or something.
Yeah,
Right, which is a different product.
So while it does that, Ray, while it does that, I compare that with the existing 7400 because the 7400 can actually do 300,000 IOPS on its own. You don't really require 7450 to sort of go against. Okay, so that's another view. Yes, kind of.
Right on time.
Any?
Yeah, let's take any last-minute questions.
Any last-minute questions?
Is there any
Go back to that
staying?
slide while we do the questions.
Okay.
Right? Because I think it is important to cover the key attributes here.
Is that a stretch or was that a question? So your hand shot right up. It looked like you.
So maybe I'll leave you guys with 4 things, right? Okay, around again the 4 themes we talked about, right? Performance, efficiency, resiliency, and this notion of data mobility. Right? I think these are the key areas that we want to go forward with, right, for our flash offerings. While we're sort of offering in these 4 key areas.
I'm curious, I don't think it was in this presentation, but an earlier presentation, you guys brought out duplication and compression as well. Is there going to be extra talk on that, covering that?
Stay tuned.
Today as well?
Stay tuned. I think that's something which we need to have maybe an NDA type discussion.
No, but I mean, it was brought up in the slides here, so okay.
So I think there are more details we'll have to go over.
Okay.
So there's actually a Siamak did it, but we had a presentation to the bloggers at HP Discover, and some of that you're probably saying is NDA, they talked about in that section, which didn't get dates, but basically summarize if I don't say this correctly, but you've got so much headroom, the ASICs can do this, it's all there to be able to do it.
Yeah, I mean, so the best way to think about it is that, I mean, so the attributes that makes dedupe possible is the size of the cache line and the size of the data blocks that you're actually, handling on the back end, right? So if you think about thin provisioning, it uses 16K blocks, right? And that is the unit of allocation that we actually allocate on disks. So if our unit of allocation was 1 megabyte, dedupe would have to find 1 megabyte entities that were exactly the same, and that's going to be pretty hard, right? And if you think about some of the other array vendors, they use sizes as big as 40 megabytes or 72 megabytes. Now trying to find duplicate, 72 megabyte entries, right? But because we use 16 kilobytes, if you finding duplicate 16 kilobytes is much easier. And we actually have data that says you can't find them, and they're there, and they're just as good as almost 4 kilobytes. We've done the actual number, 4K, 8K versus 16 kilobytes. So everything's in place to be able to actually build unthin provisioning deduplication, right? But I can't say much beyond that. Just that the architecture lends itself to deduplication.
So, are any of you guys staying for this afternoon?
Yeah, absolutely.
Okay. So let's do this because we do have lunch. If lunch is over next to Trader Joe's, okay, Trader Sam's. Is it Tarango or Tarago, whatever it is? You know where we're talking about, right next to. There's a basically you walk up and there's a screen where you punch in your order. What we need to do is just get everybody in line, and everybody's going to just place their order together. If it's not very busy, which I don't know how busy it is, we'll get in 2 lines. What I'll probably do is actually get the HP people get in line with me, and I'll pay for all the HP people and let our agency, let Ivy pay for all the bloggers. So we'll just we'll take as many as the screens we can, get lunch going. They say it comes out really quick. They say it's really good. And we'll just have lunch over there. Tom went over there to grab a bunch of tables for us. So just head on over there and we'll order lunch and try and be back. I don't know what it's going to be like there, but put an hour in the schedule. But if we can be back about 10 till, maybe we'll try and start at least getting settled in, so we can start right at 1 instead of starting at 1:10.
Calvin and QoS are lunch today. Right?
Yeah, right.
You guys are a different QoS level.
That's right. You guys are you guys are getting throttled.
Lower priority.
Yeah.
I got it.
Is it okay to leave stuff here?
Yes, they are going to lock the door, so I actually have to go find security, make sure they lock the door, so you can leave everything here. Doors will be locked, and I'll hopefully get them over here about 1/4 to unlock it. So if anything you leave in here, you won't be able to get in.
That's right. That's the reverse of that problem.